Recording. Okay, so welcome guys for this new session, and hope so we'll cover this remaining part of the week 2, which is very important part, which is nothing but your kernel PCA, which creates the base for your upcoming all kind of algorithms which shows this kind of non-linear relationship in the future, mostly in the supervised learning algorithms. That kind of trick, kernel doing the kernel and in using that output for the final decision making, so that part will be used in the supervised learning part. So if you understood these kernel sections, then you will understand the upcoming all the parts in SVM and all. So this is very important part as per like this machine learning technique subject concern. Okay, so okay, what we before that, is there any questions from yesterday's session? If you okay, 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 because if it is there, then we can solve. Otherwise, yeah, we can go ahead. Super. So we are good in numbers, not a problem. So let's start now. So before that, I will ask the, because yesterday we have seen that we are like trying to we are having something like a non-linear relationship in the lower dimension. For example, if my input is something like this. So if my input is something like this, or my input is like a circle, that time if my features showing this kind of non-linear data set, then I cannot do any kind of normal PCA. I cannot use the normal PCA here just to show the linear relationship between the points. So I can't use that type of things. So if it is like having this kind of a non-linear relation in the feature points, I need to use the I need to use our different method to do the PCA. So what PCA is having the expectation? What is the expectation of, like, what is the output of the PCA? Like we have now seen it from day one. PCA, what we are doing, we are just getting all the points. We are having lots of points here. So these points we are projecting on the line. Like we are trying to figure out some line which can show that the points are like projected on this, and then we are like compressing the data set. That main objective of the PCA is reduction in the dimension. Like you are finally you are projecting all the data points on this line, and then you are using the representative and coefficient combination to just show that the complete data set of, like, maybe if it is a 2 billion data set what we have earlier seen, then we just able to show only the 1 billion plus this representative if it is 2. So 1 billion, that much means like 50% of the dimensional reduction we achieved by using the PCA. So PCA's main aim is to reduce your number of dimensions, or whatever the dimensions you are having, you want to compress that, you are using the PCA. So what we did, we constructed the line, we figure out what is the baseline, then we projected the data points on that line, and we said that okay, now we can forget about, now we can, what we can do, we can just forget about these points now, and we will just think about their projections. So their projections are something, I'll just use here. So their projections are these. So we are now thinking about the data points there. We are just thinking about the projections, these projections, red dots, what I have showed you. So this corresponding here. So I'm not thinking about this now, the projections here. I'm just thinking about red dot. Once that red dot is here, I have now the points. Now I for representing the, or for showing you, for drawing purpose, I draw this line. Okay, just to show you that how these points are now looks like when I projected the points on the baseline. So for drawing purpose I use this line. Otherwise PCA's output, once you have like a bigger data, you compress into the smaller data. That small data now you use for the another, like SVM or another kind of a classifier. Okay, like these kind of a classifiers or anything, like for example, we use this eigenphase data demo. We saw that eigenphase demo. eigen face detection demo. What happened there? We use our PCA, and then we saw that with the principal component 1 2 3 4 how this image looks like. Okay, but that just for representing that image we saw this one, like PCA in the k equal to 62, some person's face some way, or like 362 where maybe k equal to 360, we saw some person's face here, but we don't know whether that person is Murli or Ashwin or any Preeti or anyone Tejaswini, anything. Okay, we don't know. So for that reason we need to use the another classifier, like a SVM classifier, where which has the labels saying that okay, this person is Ashwin, this person is Murli, this person is Preeti or Tejaswini, or etc. anything. Okay, so you have the labels, like you have like next stage. So next stage is your supervised learning. Okay, supervised learning. But in this point, because this week 1 and week 2, what we try to learn this till this here, till this section we try to learn. Our main aim is to bring the data for the next. This is called a downstream task. Downstream task. Like you will say na, say I want to do this one, and in my future in downstream I want to construct some business, and where I want to do this XYZ work and all. So in downstream tasks you are using the PC output for another classifiers or any kind of supervised learning to detect whether he is Ashwin, Murli or Preeti or Tejaswini or etc. any kind of person. Okay, so that's why we are trying to get the data till here from the PC. Once you get the data, you do whatever may be. So as of now we don't have next application, so what I did, I just, instead of sending to the next SVM or something, I just thought okay, I will plot that data, and so I showed you the graph. I showed you the graph with the baseline and the points here. Okay, something points here. So it is, you don't need to think that you the PCA, whenever you use the PCA you are figuring only the baseline, because the PCA will comes in the combination, like in terms of applications. If you are doing some kind of a real time projects in, or you are developing some product, so you are not just doing PCA, you are doing the combination of PCA with another supervised learning classifiers, where you are using PCA output to them, and then it will detect that. So you can directly also use SVM instead of doing PCA. But why PCA we are using? Because PCA reduces the dimensionality. Like instead of getting like 1 billion of data, 2 billion of data, you can just simply say that 1 billion. Like for example, I last time mentioned you, there is a compression what we learned. So the compression, in the compression what happened, this is something like a face of a person, and this is like a HD image, like high definition 9020 cross 1080 image. Okay, but you don't know, you don't want this much of clarity, or this much of a pixels, just to say that whether he is Ashwin or whether he is a Murli or what. So what you want, you can compress it also. So after compression what happen, it will just reduce the unwanted thing, and also it just try to maintain your face as it is, like with little bit of low quality of the image. It won't be 9020, it will be like it will just reduce the number of pixels to store that, and it will have this another image. So with that compressed image also you can try to figure out whether he is Ashwin or Murli and all XYZ work what you can do. So you can use this compressed image. So that's the reason we use PCA along with SVM. So PCA reduces the dimensionality, and once you reduce the dimensionality, you can apply the SVM on that reduced dimensionality output from the PCA, and that will help you to make it faster. Like that's why it will be faster. Actual implementation will be the faster, because the dimensions of the of input to the SVM is reduced as compared to without using the PCA. So here this is the reason we use PCA output for SVM. So this is not the point, like this is the point which you just need to remember. So in the future, like for the week 2 is over, week 3 start, week 4 start, classifier start, and all things will start. But you just need to remember that PCA output will go to some other algorithm which is using the PCA output and doing some kind of a classification. Okay, so what in this case, so in what we yesterday also, yeah. Yes. So Yeah, it will say whether he is PCA, which PCA's work is just to find out the maximum variance. So it is not showing any kind of detect. It will not show that he is Murli or he is Ashwin. It won't show anything. It will just say that there is some data I am getting where it shows the maximum variance. So the variance is like I am getting some data which has the maximum information this line. That's all. So if you want to see, yes, yes, yes. Yes, it doesn't give you any kind of how like our brain give final decision whether we have to run or we have to stay, but our eyes will just capture the things and get the signal to the brain. Okay, I captured some information, so some animal is coming towards you, some tiger is running towards you. You have to run or you have to wait. That is your brain decision. So that brain decision is something like which is already trained, saying that if something is risk you are seeing, just run. So that is what your brain take the decision. That is something like a supervised classifiers, supervised learning algorithm take the decision. PCA is work is just like I get the data, send it to the brain. So PCA is like trying to see the information and then it's reducing the dimensions, like saying that there is like thousands of dimensions. So instead of that, you just work on the smaller dimensions where it that smaller dimensions are nothing but your principal components. So instead of getting like for example that many billions of data, you are just trying to get maybe five principal components. So that is your actual principal component output, like this is your output from the PC. So that five principal component output, you are just getting that data and you are giving it to your PCA, saying that giving to the next algorithm, saying that okay, this is the data. Now I reduce the dimensions. Earlier it was like 2 billion or data. Now I am having 1 billion. You can use that data and then you can choose whatever the things you want to do. So my work is done. So like this. So this is what PCA try to do. Okay. But just because this is some point will come at the end of this week 2.5 lecture, that why we are doing something, then you will understand okay, this is what we have to do for the PCA, because PCA is not the PCA algorithm you are implementing in your product. It is coming with along with some another supervised learning algorithm. That's the reason I'm just explaining you this part. Okay. So in this point, so yesterday's point also I'm just now going to continue. So I we have seen that there is non-linear relationship in the data set, that whatever there is a like data set we have. This is like a famous moon data set, data set, where you will see the relationship between the datas are like non-linear or something. Okay, so something like this, or there are like a circles with like this data. So there is one circle here center and another circle outside, and you have to use the PCA to differentiate. That's not possible if normal PCA line cannot differentiate or cannot give any kind of a variance among the data. Okay, and next point, what is the variance actually? Okay, what is variance, because we are now discussing variance and all. So once we draw the line, we know now the maximum these points, like these points are now projected on this line, correct? Okay, and this point has like less variance because these points having this line has like less variance because the points are like projected here, which is not giving any more information in the reconstructions and all. But here these points are giving more and more information, the more variance is present in along this line. That's why we choose this line instead of this line. We don't choose this, we choose this line. So what is this maximum variance? Because for example, is it like till here or till here or till here? Yeah, so this is like a what is actually the maximum or what is the variance here? So why, which value shows this variance? Is there any variance, like because here also there is this variance we are saying for this another line here, we said this is a variance. I'm just drawing this one here, this kind of a things, or this green line we have just draw here. So this is like a variance, but who represent the variance here? Because you know that there are covariance matrix and eigenvector, because you know now this direction is shown by your eigenvector, correct? Eigenvector. But who showed this kind of a data? Why this data is darker, means like why the more variance is present here? This is shown by your eigenvalue. Okay. Yes. So variance is given by your eigenvalue, and variance is present along the eigenvectors. So if somebody asks you this variance now here, so firstly what happened, we calculate our matrix A B C D, and then you calculate these eigenvalues. So maximum eigenvalue corresponding to the maximum eigenvalue, you are having eigenvectors, correct? You are having that these are the eigenvectors for your, that which is nothing but your principal component, pc1 or pc2 or that. Okay, so that is the principal component. So the maximum eigenvalue is nothing but your variance. That is what your variance, that is the variance, like how much spread is happening. So you will say that this line is, this line is having, okay, maybe I'll draw here, this line is having this much of spread. So means their variance is only this much. If you say another graph, I am having another graph with more variance, like more spread of the line. So this has a more variance, means if the eigenvalues are like this, because of eigenvalue, that eigenvalue show that how much spread happen in that, on that line. That is called as variance. The eigenvalue represent your variance. Okay, that eigenvalue represent the variance. So maximum eigenvalue give you the eigenvector, and that eigenvector give you the direction. Like, so you don't know, for example, these points are like here. Okay, these points are like here. Okay, where, yes, lambda, no, lambda is eigenvalue, w is eigenvector. Yeah, yeah, you can see av equal to lambda v. So lambda is equal eigenvalues. Okay, and that variance is nothing but your lambda. The variance is nothing but your lambda. That is lambda, that is nothing but your eigenvalue. Okay, okay, variance is nothing but your lambda, that is your eigenvalue. So that eigenvalues give you how much spread happening on that in that direction. So this is the graph. So I am just having some variance, like I am just showing the variance. I am not drawing any line here. Okay, I am not drawing any line because this all are like now here. For simplicity, maybe earlier what we did, like we draw the lines and all, but if you don't have the line, so this is like variance, and in another directions you are having this kind of variance. Okay, this kind of variance, or maybe another there is another directions, I am having this kind of variance, which is having less variance as compared to the red one. Yes, yes, yes. So whatever the direction shows you maximum variance, that is what you want. Like that is actually, because this lambda has this many variance, this much is the variance, like giving the maximum length. Okay, next this blue color lambda dash has some kind of variance here, this direction, and the green color lambda double dash or lambda 3 dash, or maybe, okay, this is another variance. So you will choose the variance which is the maximum variance. So you will not choose this, you will not choose this, you will choose this one which has the maximum variance. So this is what, and that corresponding to that lambda, okay, eigenvalue, you will choose the w. What is that w? It will just say that, okay, this is the w eigenvector I got, so I have to plot the line passing through that, or it's like showing the directions of the line which is passing through that point. So that's all. So that is what your baseline you mentioned, that is what your baseline. Okay, so this is the important concepts we will use in this lecture. Okay, so just to have you the understanding what exactly we are checking. So that's why I just explain you what is this variance is nothing but same, like it's the same what you know already, but I just want to give the recap of this one. Okay, so in this non-linear relationship things, when there are like for example, as I give you the earlier example, that in the lower dimension we saw yesterday, f1 and f2 are the two features. Okay, f1 and f2 are the two features, and this 2D feature I am now projecting the 2D feature into the higher dimension, which is like a 6 dimensions. And we saw that what are the 6 dimensions: 1 f1 square, f2 square, f1 f2 and f1 and then f2. 1 2 3 4, this is combined 5 and this 6. Okay, that's why you are projecting 2D features which are showing something like circular things like non-linear relationship, and you are just projecting into the higher dimensions, and that higher dimensions, once you calculate, it will become like a plane. If you unroll that, if it's become like a plane in the higher dimensions. So plane is something like the linear relationship in the higher dimensions. Okay, you can maybe check later on the video, our yesterday's session, you will understand that. So because this is something what we learned yesterday. Okay, so what happened, because these 2D points, I am now projecting 2D points on the higher dimension, like a lower dimension to higher dimensions, I am projecting that point. But sometime what happened here, what these points are saying that, okay, this point I said that, okay, I want only the power of 2, like p equal to 2 projection. Like I'm not going for the p of cube or f3 or f4 or something. I want only the quadratic relationship. For example, if I want a cubical relationship, that we have also seen yesterday, but I will just revise now. So there are like a feature f1, f2, f3 and f4, like these are the 4 dimensions I am having in input. Okay, in input itself. Earlier for the circle, what happened, I have f1 and f2. Okay, but now I am now having 4 dimension in the input. Instead of 2D, I am taking now the example of 4D. Okay, so I want to project that 4D points. I want to project that 4D points. These are the lower dimensions. Okay, this is lower dimension. I want to project that 4D points into the higher dimension. I want to project the lower points from lower dimension, like 4D points, into the higher dimensions. Maybe we are having like a cubical relationship there, because earlier we saw that quadratic relationship where we have like a f1 square and f2 square or f1 f2. So if you see that their value is like 2, that raised equation, this one is 2. Okay, so here we are trying to see the cubical relationship or the cubical power relationship. Okay, so for example here cubical, okay, how this one is f1 cube or f2 cube or f1 f2 f3. Okay, or you can maybe take f1 and f1 and not f2 square, but yeah, we can take f2 square also. But here something like you are trying to seeing the cubical relationship of the points. So here you will get clear idea. Okay, so I am trying to project something from the lower dimension to the higher dimensions. Here this is a higher dimension. Okay, I am trying to project this 2D relationship into 6D. This is higher dimension. Okay, and this is lower dimension. The lower dimension has the same graph is in non-linear fashion. In once I go to higher dimension, it become like a linear one. And once it become linear, you can use PCA on that linear graph here. Okay, this is what our intention. So now I am trying to do the 4D here, like instead of 2D I am having 4D. So what I will do, I'm just want to project the data like on this, because the feature map, whatever the feature map I am having, the phi of x, so the function, so I am having these coefficients. So I need to project here like f1, f2, f3, f4. So when you want to project on 3 cubical relationship, so that means that you are considering one like a power of 1, p0 also, p1 also, p2 also and p3. The maximum raised to equation, like maximum terms or maximum coefficients will come as a power of 3. P2 will be there, p2 will, p raised to 1 also will be there, p raised to 0 also will be there, and p raised to 3 also will be there. But there is no p4 because we are expecting only the cubical relationship. So here what happens is, here we consider degree 0, degree here 0, like power of 0 is 1, that's why this degree is 0. Here what, degree 1 term, f1, f2, these are separate terms. Okay, separate. And here degree of 2. Okay, what is the degree of 2? f1 f2. Okay, here, and then f1 f3, because our input is here. f1, f2, f3, f4, these are your 4 dimensions, and out of that you are choosing only the cubical relationship. So I'm checking f1, f2, f1, f3, and then f1, f4, and then f2, f3, then f2, f4, and then I will write here also, and then f3, f4. This is what this is like a degree 2 terms. Okay, these are the degree 2. Okay, and these are the degree 1 here, degree 1, degree 2. Now what I need, because I'm considering only the degree 3 cubical relationship, means degree 3 only. I am not interested into more degrees. Okay, so I'm projecting this 4 dimension input to the higher dimensions. But how many higher dimensions? I know about this 2D. This 2D I am projecting to 6D, because that what I have calculated earlier. Okay, in the yesterday session we know that now 2D is projected to 6D. But if it is 4D, how many D's I want in the higher dimensions? I don't know, because here in earlier case 2D is projected to 6. So there are 6 terms we are having in higher dimension. But when it is having 4D in the lower dimensions, how many terms will be there in the higher dimensions? That we are checking now. How many? Because you simply can't say I am having 11 terms. No, you have to see that how many terms will be there in the higher dimension. So that's what we are now calculating. Okay, so when you are saying cubical relationship, you are going degree 0, 1, 2, and also degree 3. Okay, in the degree 3 it will be something like f1, f2, f3, one value, then f1, f2, f4, another value, then f1, f3, f4, one more value is f2, f3, and f4. Okay, only these 4 you can get if it is like a degree 3. These 3, this C, this C, and this C. Okay, this is degree 3. Okay, degree 3. Okay, so if I just calculate how many coefficients or how many parameters I need in the higher dimensions, I know for the 2D I need 6 values, 6 values in the higher dimension for projecting 2D values to 6D. But what will happen if it is a 4D in the lower dimension? How many I need, how many values I need, how many coefficients I need? So here we can see, so here what, out of this 1, 2, 3, 4, this f1, f2, f3, f4, out of these 4 I am choosing here. So for the constant it is 1. For this 1, 2, 3, 4, I am choosing 4 out of 1 value. Okay, 4 out of 1. From here 1, 2, 3, 4, 5. So here 6. So if you see these values, like these are actually the permutation combination. 4C, out of this I am choosing the degree here 2, because these are the 2. 4C, because I have already calculated it, so I am showing it here, because the 4C2 is how much? This is coming as a 6. So that's 6 value, 1, 2, 3, 4, 5, 6. So out of 4 I just need the combination of 2, like degree 2. So 4C2 is 6. And what are the 6 values? 1, 2, 3, 4, 5, 6. Okay, these 6 values, these are the degree 2 6 values. For if for degree 3, so for degree 3 I am using 4C3. What is this? 4C3 equal to 4 values. So what is that? 4 values. These are the 4 values here. These are the 4 values here. 1, 2, 3, 4 with a degree 3. For degree 2 I need 4C2, which is nothing but 4C2 is how much is that? We have calculated 6. Okay, for single 4C1, how much is that? It's 4. And this constant is anyway 1, or we have 1. So here, so if you do the calculation now, 1 plus this 1, 2, 3, 4, 4C1, how much? 4C1 is 4. This a 1, 2, 3, 4, 5, 6, you got 6, and this 1, 2, 3, 4, you got 4. So total 15. So if you want to project 4D points from lower dimensions, okay, 4 dimensions in the lower space, if you want to project in the higher space, you need 15 dimensions. You need 15 dimensions. Okay, so here what happen, if you are having D features, like now I have one f1, f2, f3, f4, these 4 features. So this is 4D, like D equal to 4. But if I am having, in general, if I am having D features and I want to project, and what here what happened here, I want a cubical relationship, like cubical. Okay, cubical relationship means I need power of 3, correct? So if I am having D features and I want to project on the power function like pth, power relationship, like I want pith power relationship, then how many we need, the how many we need is coming like summation of, and see we don't want only p3, we also need, like we have seen that here we also need p2, like degree 2 p2 and degree 1 also and degree 0. So when you say that I am projecting into the higher dimension with the power 3, like I'm interested in the cubical relationship, or I'm interested in the fourth relationship or fifth relationship. So you are not only just want 5 4 3, you also want the lower dimension 0 1 2 3 also, 0 1 2, or if you want 4 then 0 1 2 3 and 4 also. So you need to see like this one is equal to d should be, the dimension should be less than or equal to pth relationship, means you are, if it is a third relationship you want, so you need to take 0 1 2 and 3 also. Okay, 0 1 2 3 also. So here this equation, this gives you the because sometimes the question may ask you are projecting the d features, like two features on the in the higher dimensions, how many features you want in the higher dimensions, how many features you need in the higher dimensions to project the lower dimension d features. So the formula is something like, because here you have seen that one, how we got one is like 4c0 plus 4y4 here 4c1, and then 6, how you got, you are having 4 features, you are choosing 2 features, and then how got 4, you are having 4 features, you are choosing 3 features. Okay, so here what happened, the 4 is what, 4 is your feature, like d feature. Okay, because d is equal to 4 in this case, d is equal to 4. Okay, so here d is here, so you are choosing c. Okay, combination, permutation, combination, what you know that. Okay, and what is here, I is 1 0 1 2 3, so here I, so this is the formula. This formula gives you how many features do you need in the higher dimensions to map the lower dimension data. That formula gives you the number of features in the higher dimensions. And if you see the complexity of that, if you see the complexity, because we know the complexity of PCA, I'm just giving some history what we learn. It's a d cube. Okay, for the PCA, just this is not related to here directly, but I'm just simply saying. So the complexity of calculating this number of features for the higher dimension is actually your d dimensions, whatever your d dimensions you are having, raised to p. Okay, d raised to p, this, oh sorry, I'll just properly write. Okay, so the complexity of calculating how many features do you want in the higher dimension, it's simply what, because the normal example I gave you, this cubic relationship with the f1 f2 f3 f4, it gave you 15 data, 15 feature points in the higher dimensions. Okay, 15 feature points in the higher dimension, that's okay, because it's easy to calculate that 4 dimensions in the lower dimension 4d you are projecting into the, so this d is like a lower dimension. Okay, lower dimension is represented by small d, and capital D is represented by higher dimension. Okay, higher dimension. So in future, if I'm writing small d and capital D, you just try to understand, like small d is for lower dimension, capital D is for higher dimension. So it's easy, like 4 dimension lower dimension value 4 is now projected to a higher dimension with a feature of 15. But if I am having, for example, if I am having like a 15 features in the lower dimensions, and I want to project in the higher dimensions, what will be the value? So that's really difficult if I'm just going with these kind of calculations and drawing the f1 f2, the f1 and these value. If it's very time consuming, and it's not that much easy if I want to go with that. So for that reason, here if you see, if your d is equal to 15, so and you are interested in, like earlier this was a cubical relationship 3, but now for example your d is 10, consider your d is 10, and you are interested in the p equal to 15, like 15th relationship. Okay, 15th relationship. So what will be the time complexity? The time complexity is like a 10 raised to 15. So this many features you want in the higher dimension, like whatever the lower dimension data you are having, you are trying to project into the higher dimension data. And how many higher dimension data you want? This many, Like now in bottom you are having only 10 features. Like for example, these are the 10 features here, and you want that many features. How many? Like 10 raised to 15, that many features. Like this is the complexity, that much complexity you need to, like that much number of cycles, or we can say like that much time consuming, that if you want to actually do that calculation and get the data. And if you really want to do, you can just put like d is what here, so d is 10, and then you have to do like all these summations of 10c1, 10c2, like 10c3, and all, like you have to do everything here, okay, till p. Okay, so like this you need to calculate. So that many features you want in the higher dimensions. But is it like comfortable to do this? Like if we are having something, because what we are having some x data set in the lower dimensions, and you are like saying that I want to project into higher dimensions, which is phi of x. Okay, so creating the lower dimension, having lower dimension and projecting to the higher dimensions with the phi of x, with how much is that dimensions of this is like rd. You are having here, this dimension is small d, and you are having this capital D is the higher dimension. And what is this higher dimensions you are calculating? Like this, the summation of I equal to 1 to 0 to p, and this d c I. So this is the summation. So that much, it's not that much easy, it's really very hard to compute this kind of a compilation computations. And if, and what finally we'll do, like to get the phi of x, you have to do these kind of operations. Okay, to get this phi of x, you have to do this kind of a big computation. It's not impossible, it is possible, but it is really time consuming. Okay, and once you, for example, once you get the phi of x, what you are doing then later on, you are getting this eigen direction. How you are getting the eigen direction? Eigen directions with the covariance matrix, which is nothing but phi transpose x into phi of x. This is how you are getting the eigen directions, like the directions what you want in the PCA, like these directions. And then you will project the data on this line, and then you will say, okay, I am able to now compress the data. I have reduced the dimensionality. But what, on what basis you are doing that? You are calculating phi transpose. This is a higher dimension. Okay, lower dimensions in normal PCA you do x transpose x, that k value what yesterday we have seen. Okay, if your d is greater than n, that time you are doing x transpose x, and then what you do, then you get a beta eigenvalues, eigenvectors here, eigenvectors, and then you get n lambda, that is eigenvalues. And once you get beta, then you need to calculate your alpha, which is like beta divided by under root of n lambda. And once you get alpha, what you do finally, you calculate w by choosing your data points into your alpha. This is what our issue one solution when d is greater than 1. So same way, if, because this is where you are having linear relationship, but now in our current case it is showing non-linear relationship, because it's not linear relationship. So what we did, we are having because in lower dimension it is saying x transpose x, and what will happen in the higher dimension, because x is now, this x data is now projected into higher dimensions, is now moved to the higher dimension. This x data is now moved to the higher dimensions. Lower dimensions it was like a circle, and higher dimensions it is becoming like a plane. You are totally unfold that data. Okay, so it become plane, and once it linear, you apply PCA on that. Means you want something in the higher dimensions. Okay, so PCA, trying to do PCA on higher dimensions means you are trying to calculate the eigenvector. How you get the eigenvector in the higher dimensions? You have to calculate like this, like how we did here, k is equal to x transpose x. So same way in the higher dimension, x is replaced by phi of x transpose into phi of x. This is the way how you need to do. But getting phi of x, what you need to do? For getting phi of x, you are calculating how many terms are there in that. So you are trying to figure out d, this is this many terms, this many operations you have to do, which is nothing but the complexity is nothing but d raised to p. So if you are having 10 features in the lower dimensions, you are getting 10 raised to, and you want to project on the 15 dimensions, that much is the time complexity, which is not at all good idea. It is like totally time consuming step. So you cannot simply go in the higher dimensions and calculate your eigenvectors using this formula, because calculating phi in the higher dimension is not at all accepted, or is not at all good idea, is not a good idea to calculate phi of x. Okay, not good idea to calculate phi of x, or phi transpose into phi of x, because this is what the final you will get the reason, because phi of x calculation shows more time complexity. So phi of x, not exactly phi of x showing more complexity, because indirectly phi of x need what, the number of dimensions, how much dimensions you want, and that actually that part shows the more time complexity, like which is nothing but your d raised to p, that is the complexity showing. Okay, so you should not do something like this to get your phi of x. So once you don't have phi of x, so okay, so you don't have now phi of x, what to do? You don't have right now phi of x, and you want to get the your best line by using the eigenvectors, but right now you don't have phi of x, means you cannot like do the PCA in this non-linear case. So what is the actual things that we will see? Okay, so any question till now here? Murli sir, anything? Hello. Okay, okay, okay. Before that, you understood now, because sometime in, if you watch a movie, what they will show, they will show the current situation, what is going on and all, and they will then immediately bring it to the history, something like what happened in my history, and they, somebody show that their history and then come back to their current shot. So something like this. So what now I mentioned you, we have a issue calculating phi of x. Phi of x is nothing but your whatever the like the feature map, whatever the feature points you want to calculate in the higher dimensions, that having more complexity, that is not easy for you to get that particular of a data from simple calculation. So you are having some kind of now the roadblock, and that we need to find out some solution on that. Okay, so in this case, that feature map calculation, before that I'm giving you some like basic, like last time we have seen that linear algebra fact. So linear algebra fact, we got that the eigenvalue, non-zero eigenvalue of x into x transpose is same as x transpose into x. These are the feature facts what you understand. Okay, so here there is another point we need to understand. Okay, for example, okay, this is a important concept you need to know. Okay, you are having a capital X matrix. Okay, and this is your data points or data set. Okay, and each data set now having, I mentioned earlier, like x1, x2, okay, and x3 for example. Okay, what this x1, x2, x3 is saying, this x1, I said x1, so what is this? This is nothing but, that is each one data point. This x1 is this column, that is the column is a data point. Okay, this is one data point. How, what is this x1? X1 is, for example, here in this case I will take one example of x1. Yeah, so this is something like, for example, 1 comma 2. Okay, x2 is 3 comma 4, x3 is 5 comma 6. So what here, d is how much? 2 dimensions, and how many inputs I am having? 1 2 3. So n is equal to 3. Okay, n is equal to 3. So how this matrix looks like, x become, now x looks like this. So we saw now x1 is what? X1 is 1 2, x2 is what? 3 4, and x3 is 5 6. Okay, it is 2 rows and 3 column matrix. Okay, and someone ask you, like, like in PCA generally what we did X transpose X. So if I just try to see X transpose X, this work, so what it will be 1 3 5, that is X transpose 2 4 6. Okay, and then it is 1 3 5 2 4 6. Okay, this is like a 3 cross 2, 3 rows, 2 matrix. And what happened here? 2 cross 3. And if I just calculate this one, so it will give me final 3 cross 3, which is like 5 11 17. Okay, 11 25 39 17 39 61. Okay, which is like a 3 cross 3. Okay, so it's easy like to get the X into X transpose in this normal PCA whatever we have done, and with the linear relationship. Okay, here linear relationship between the feature points. Okay, that's why it's easy to do X transpose into X. Okay, that's good. But if it is having higher relationship, that's the main issue. But just be here like with this example. So X transpose X is what you calculate, 3 cross 3 matrix you got. So instead of that, we can use another way to get the same matrix. How we can do the another way? So for example, so here this is X transpose X. Okay, so X transpose I am writing here. Okay, X transpose is what? X transpose is 1 2 3 4 5 6. What is the first row? This is row 1, this is row 2, this is row 3. Okay, and for X, what is the row? X having row 1 3 5. Wait, 1 2 3 4 5 6. Okay, so this is what the X row, X matrix. Okay, so what I want to do is here, instead of calculating directly this matrix by this kind of a multiplication X into X transpose, I will try to do by the pairwise multiplication. Okay, I just want to do pairwise multiplication, just like what I want to say. So if I see the pairwise or element wise, well, if I want to do the element wise or pairwise multiplication. Okay, because this is a point which you will understand, you need to use in the PCA here, kernel PCA. Okay, what you are doing here, the pairwise multiplication. Okay, which is nothing but I will write element wise your dot product, element wise dot product, because this is something X transpose X is directly you got two matrix and you directly multiply, you got that. So I am not taking now this complete like the say this way dot product. I just want like element wise this dot product of X transpose X, how this looks like. Okay, how this looks like. So your row 1 of X transpose is what? Row 1 of X transpose. So I will write here your row 1 of X transpose, row 1 of X transpose is what? 1 2. Okay, 1 comma 2, and the next is X. Okay, because you need to multiply that, so X transpose into X, so it will be 1 2. Okay, this part. Okay, so what you will get? 5. If I just do 1 2 with the next 3 4, you will get 11. If I just do 1 2 with 5 6, I will get 17. Okay, similarly for the row 1, it's row 1. Similarly, if I do for row 2 of X transpose, what will happen? 3 4, you are multiplying with once again 1 2, which is 11. 3 4, you are multiplying with the next 3 4 same here, which is nothing but your 25, and then 3 4 you are multiplying with the 5 6. Okay, 5 6, you are getting 39, and I will not now do calculation, I will directly write the answer. Row 3, you will get something like 5 6 1 2, which is 17 and 39 and 61. Okay, so you are directly getting the values by doing the element wise if I do the element wise dot product of x transpose x, here this dot product element wise I am not doing, and if I just then finally put the all these things together, so here if I just do now, I'll use another case here. If I just say x transpose x of I comma j, okay, if I just say like this, this is nothing but saying x transpose of I into x of j. I am just saying this value x transpose is taking I and this x is taking j, so like this. So how this is like a, this is what, this is the index of first data points, index of first data point or the ith data point, okay, ith index, or ith index of first data point, and this, yes, but this concept will help you in the now next whatever I am going to tell you. Okay, so this is the jth index of second data point. Okay, so if somebody will ask you, can you did you have like a x transpose x of what 1 2, means what you are saying, x transpose of 1 into x of 2. So what is this? It is giving you, okay, what it is giving. So if you see here, this is saying that first row of x transpose, this is, I means here first row of x transpose, and the second value here means this value, second value of x, that is 3 4, and what is the value here, 11, correct, 11. So if I say you now like x transpose of x of for example 23, which is nothing but x transpose 2 into dot product with x of 3. What is this? X transpose of 2 means you are going to second row, x transpose second row, okay, second row, which is here, and third is what, this is your second and this is your third. How much is 39? Okay, so this way what happened now here, and if you see now our calculated earlier matrix also, if you see now, this is your calculated matrix here, this is the calculated one, correct, earlier calculated, directly calculated x into x transpose, which is directly calculated, which you are having this value, and now pairwise we have calculated like this way, okay, x transpose into x of 1 comma 2, this is a pair. Okay, so you got 11, like first row second column 11, you got correct. Here second row third column, this is second row third column 39, see 39, this is also 39, means instead of calculating x transpose x directly this way, like a 3 cross 2 multiplied by dot product with 2 cross 3, instead of calculating this bigger 3 cross 3, what you are doing now, you are concentrating on the pairwise, element wise, pairwise, this kind of a dot product, pairwise these dot products are the best option, are the, like here in this case pairwise dot products are the chosen one in PCA. Okay, so in PCA means in the higher dimensions, okay, in higher dimensions in the PCA, okay, higher dimensions. So why we are now, why I want to give you this example. So I hope this example you got it, like this is the main concept we will use. You got this example, what we are doing now here, Murli sir? Okay, so instead of doing x transpose x directly with the 3 cross 3, what we got it directly because it's like lower dimensions, easy to calculate, 3 cross 2 into 2 cross 3 get 3 cross 3, it's very fantastic, like you are happy. But what is this? This is like a linear relationship, that's why it's easy. But now you are projecting that point into higher dimensions, your matrix will also go on increasing, and if your matrix is this much big, okay, and this is one more, can you do this kind of a direct calculation? You can't do that if it is too big, if the matrix is too big with higher dimensions, you cannot simply do the dot product of this way. So instead of doing that, what you are doing, you are using this trick. X transpose X of 1 comma 2 means what? You are having one, you are already having one matrix here which is X transpose, and you are having another matrix here. Okay, so you are just going to that row of the matrix, like a first row. What is 1 comma 2? Say go to the first row of your X transpose, and what is the next element? Say 2. Go to that second column of that X2, whatever the X you are having, that second column. So you will just go like, I just put reverse, like you are seeing like this here. Okay, maybe I'll just remove this part. Okay, so just consider this one here. Okay, so I am interested only, instead of calculating the bigger X into X transpose, I am just now interested in this row of X transpose and the column of your X. I am just using that multiplication to get your actual data of phi transpose X into phi transpose. So here what we are now coming to the point, one important point, what we are now coming. So what we are doing here, what we do, we are having xi data, like what I mentioned, like X transpose into X 1 comma 2 for the example I took. So you can consider X transpose X I comma j. Okay, so that is nothing but X transpose I into X of j, these value, ith row of X transpose and jth column of X. Okay, and then the dot product of that, and that will give you one value, and that if you do it for complete points, you will get the final matrix. Okay, the final dot product. Okay, but here what we are doing, whatever the xi data you are having in the low dimension, okay, and xj data in the low dimension, you are projecting the data to higher dimensions. So whatever the xi's higher dimension is, phi of xi, whatever xj's higher dimension is, phi of xj. Once you get this data as an input, you are having this one as an input. Okay, this as an input, you are passing this input and calculating what, because you need to calculate your eigenvector. So what you are doing, xi into phi of phi transpose xj, and you now understand, you have to go from this lower dimension, this is a lower dimension, you are going from this lower dimension to the higher dimension, and once you are in the higher dimension, you are sending it to the calculating this w phi of X transpose into sorry, this is not the, okay, you are calculating phi of X transpose into phi of xj. Okay, you are calculating this one, that's all. And what is that? This is nothing but your covariance matrix, and once you get a covariance matrix, then you calculate your eigenvalue, eigenvector, and the principal component, and much like baseline you will get that, that's all. But this is not the end of the story. The problem comes here. As you are getting phi of x and phi of xi and phi of xj, then you do this kind of multiplication, and we observe that calculating phi is the bottleneck. That's the problem. What is this? You need to find out number of dimensions that we have seen with the complexity of what, O of d raised to p. If you need in the feature like higher dimensions, you need a power of 15, and you are having 10 dimensions, 10 raised to 15. It's like a time consuming, it's not at all accepted. So you should not do the phi calculation. If I don't do phi calculation, then how I can just go with this phi transpose xi into phi of xj? How I can go there? So what is our now the main aim is, our main aim is, can we just bypass, can we skip doing this process and directly jump here? Can we do that? That is what the main aim. So instead of calculating phi of xi and phi of xj, which is what we have seen, calculation of phi of xi and phi of xj is nothing but you need to calculate number of dimensions in the higher dimension number of features in the higher dimension, number of features in higher dimension, okay, that is having complexity O raised to d raised to 15. So 10 features and you want a 15th power relationship, so that's like a chaos, you can't do that. So we don't want to do this phi of xi and xj calculator. So is there any way that we can avoid calculation of phi of xi and phi of xj in the higher dimension and directly jump from lower dimension of xi xj directly to this equation, that what we just wrote here, this equation? Can we do direct? Is there any direct path for doing this instead of this doing xi and xj? Okay, so I want to check, can I go directly to the dot product of, because this is what I am doing, this is dot product calculation, xi into, so I am interested, like I want to check, can I go directly to the dot product of this phi of xi transpose into phi of xj instead of calculating the phi of xi and phi of xj? I don't want to calculate phi of xi and xj, but I want to do this. Is it possible to calculate dot product? That is what is the heart of your main thing in the kernel PCA. Okay. So is there any issue, any question till now here? Like nothing more happened, but we are like going towards the point. But I mentioned the what is the problem in the phi calculation, the feature map calculation. We need to get the number of features in the higher dimensions, and the number of features, getting the number of features in the higher dimension is the having more time complexity of d raised to p. Like if you are having d features and d equal to 10 and p equal to, you are having p like 15th relationship you want to show, so 15th power relationship, so 10 raised to 15 is like a huge, so it's like time consuming and it's not preferred way of calculating phi for that, like it's difficult to get the feature map, because we have seen yesterday that I am having this f1 and f2 and its feature map is what, this phi of x is what is, phi of x is, yeah, 1 f1 square f2 square f1 f2 f1 and then f2. This is the phi of x of this x. Okay, but what is the phi of x for the higher dimensions? That's the problem. So it is very dangerous to get the phi of x for this, phi of x for the data which has the number of, like in lower dimension, if the feature is like a 10, here the d is equal to 2, but in, for example, in feature is different, so then it will be d raised to p. this is the more, like how you can get is something like here what I have said, d choose of your I, and I is equal to 1 to n, 1 to p, sorry, 1 to p. So this many features, if you just calculate, then this many features you need to get in the higher dimension, then the time complexity for getting that is d raised to p. Okay, this is the main thing. So phi of x calculation is a dangerous thing, but we just don't want to do now phi of x calculation, so we want to bypass this operation, calculation of phi of x. We just directly want to jump to the calculation of the phi of x transpose, phi of xi transpose into phi of xi. Is there any way that we are going to check? Okay, so to get the solution, of this problem, now we are now moving towards the one by one example, like how this we can do, we can achieve this. Is it possible to achieve this? For finding this solution, we are now checking this one here. Yeah, so first example we are considering, I am just considering first example, means I just want to do phi of xi transpose to phi of xj, this dot product. I want to calculate this dot product from xi and xj directly from the lower dimensions without calculating separate phi of x and phi of xi and phi of xj. So for that I am just considering first example. Let's take your x equal to f1 and f2, easy, normal. Okay, and x prime equal to g1 and g2. I'm taking some example, okay? And consider your function here is x transpose x prime plus 1 square. This is your lower dimension, that's why this square is showing its non-linearity, okay? Is showing the non-linearity. This is your function, and that function you want to project into the higher dimension. This function you want to project into the higher dimensions. Like we have seen, the equation of the circle is f1 minus a whole square plus f2 minus b whole square equal to r square. So that was our function in the lower dimension, and then you project it into the higher dimension, and then what you got is like something, that time you got is f of x transpose f5 of x, because something like this you got, and that is nothing but what, that is the linear relationship in the higher dimension. So now instead of this circle function, we are considering another example which has the x transpose x prime. So okay, this is a prime, okay, x transpose x prime plus 1 whole square, okay, this is our function. So if I just see, because x transpose is what, so I already having this these values here, so I'll like f1 f2 and then g1 g2 plus 1 whole square, okay. So if I just see is what is this, so it is like a f1 g1 plus f2 g2, okay. I'm just doing the dot product here, f1 g1, okay, plus 1 whole square, okay. So this is something what now our main idea is, what we want to do, our main aim is, we just want to calculate phi of x transpose this value, we just want to do this calculation, okay, phi of x transpose xi transpose into phi of xj. So what that gives you, that gives you something like, this is like a coefficient matrix, this is like a covariance matrix in the higher dimension, correct, matrix in higher dimension. You saw yesterday that k is what, x transpose x, you were doing it, correct. But now the same thing, what happened in the higher dimension, it become this become k, but higher dimension it's a lower dimension, this become phi of xi transpose into phi of xj, this one, okay. You want to do that, and you are having input as xi and xj, okay. So for that reason, now we just take one example, there will be another examples. So like circle example we took yesterday, this f1 minus a whole square f2. So we just try to project that data, like this 2D data to f what is that, f1 comma f2, and then you project it into 6D what, 1 f1 square f2 square f1 f2 then f1 and then f2, you project it to 2D to 6D, okay, like this you did it. But now what we did, we are now considering another function called as this polynomial function, x1 x transpose x prime plus 1 and whole square. It's because it's a non-linear, we want to show as a non-linear relationship, that's why we did square of that. So this is just the example we are taking, there will be different, so many examples also, but we are considering. Okay. This is, for example, you consider this as when you do this kind of a multiplications now. So if you do x transpose x and x into x transpose, like more or less their like values, if you actually see that it comes same. So when you trying to write the dimension will be different, like the eigenvalues will be same, but if you try to do some kind of computations, it will be something like instead of saying I am taking x transpose and then x transpose I am saying that this is like here, okay. But this is something like a normal in our calculations, we consider like this. So if I'm saying x transpose, it say same like in x transpose here, instead of saying like this, so here, so x of x transpose and then x transpose of I, something like this, plus 1, okay. So this is just one example I am trying to show, so it's easy for me to do the multiplication, okay. So that's why it's f1 f2 I just showed like this, and here g1 g2. So if you see here, the xi is not the g1 g2, but I'm just transposing this one here. So you can consider the x transpose plus 1 here whole square. But the main aim is to make it like this way. Okay, f1 g1 f2 g2 plus 1 whole square. Okay, this is just one example v2. And what we are doing now, so whatever the equations you are now having here, f1 g1 f2 g2, okay, so whatever this equation you are having, you are trying to solve this. You know that a plus b whole square is, what is the equation, like a square plus 2ab plus b square. So a is what here, so I am just considering now f1 g1 plus f2 g2 whole, this as a plus 1 as a b whole square. So if I just do the calculation, so what I will get finally, like if I just do the square of this and all this way calculation, so I will get f1 g1, okay, maybe I will just do this calculation here, f2 g2 whole square plus 2 into f1 g1 plus f2 g2, then into 1, that is I no need to write, plus 1 square, which is 1. Okay, and if I just now if I just do this inside this one, this is what a square, but this what f1 g1 plus f2 g2 whole square is what f1 square g1 square plus 2 into f1 f2 g1 g2 plus f2 square g2 square. Okay, and this is what plus 2 into f1 g1 plus 2 into f2 g2, and that 1 as it is. So if I just rearrange this equation, I will get something like a f1 square g1 square. Okay, I am just doing just to see, because when you see this video later on, then you will understand. So this is what here I just did. Okay, so if I just rearrange this equation, what will happen? So here f2 because see f1 g1 square, here I am writing f2 square g2 square, here g2 square I am writing here, then this one I will write first here. Okay, then 2 f1 g1 2 f1 f1 g1 f2 g2, okay, plus your 2 f1 g plus 2 f2 g. Okay, these many terms. Okay, so now because what this is some kind of a multiplication, you can see. Okay, but if I just want to separate out f1 term, I'm just trying to separate out the f1 term. Okay, so here f1 square, what is this here, this is f2 square. I'm just separating out, I'm just trying to write in different vector form. Okay, vector form with the f1 square f1 vector here, and then g2 vector will be there. Like I'm just separating f terms. Okay, and one as it is here. See this f here, this f2 here, one as it is here, and next will be your here 2, but I will write under root of 2 as of now. I will tell why, f1 and this f2. Okay, then later on under root this 2 is here, under root of 2 f1, and this square root of 2 f2. Okay, this is your f term. So what happened with the g, now g term. Okay, so if I do now g term, so here if I take g1 square, okay, then what happened here, g2, maybe I can use some other color here, g1 square, oh, no, not good, I'll let me use this same, g2 square, what this 1 as it is, this one more root under root of 2 g1 g2, what is here, under root of 2 g, sorry here f1 g1 f2 g2 f1 g1, and what here, under root of 2 g2. If you see these are the two vectors I have written. Okay, instead of writing this f1, like I got f1 square, this complete equation, I got this big equation. Instead of doing this writing like this equation, I wrote in this vector form. So if I do the dot product of this, what it will give? F1 into G1 square. I'm just writing now here in different color, just for your understanding what it will give. F1 square G1 square, okay, F2 square G2 square. What is this? 1 1, this one and this one. This is just dot product, okay? This is dot product. 1 plus under root of 2 and this under root of 2. So under root of 2 into under root of 2 is like a 2. So what 2? Here 2 we get. So these two what we are now interested. And then F1 F2 G1 G2. Later on this under root of 2 in F1 into under root of 2 G1, which is what? F1 G1. Then last one is 2 F2 G2. Means what? These two vectors, this vector and this vector, if I do the dot product, I am able to see this same equation. Correct? I am able to see the same equation. So what does that F1, what does this F1 and F2 and 1 and these complete term called as? This term, complete term called this one. Because we saw that I gave you the example of 2D and 6D. I mentioned that F1 F2 and what is that? Phi of x. What is that? Phi of x, the feature map. It was 1 F1 square F2 square, then F1 F2 F1 and then F2. This is called as a feature map. Correct? This is a feature map. So whatever now we are observing here, this whatever now we are observing, this line, this part or this part, these are the feature maps. What is this? This is nothing but phi of x, okay, and then its transpose, and here this is called as phi of another x prime, because this is G, because we know that this, we consider this value x transpose F1 F2 and x prime is G1 G2 here, okay. So this is what? Phi of x transpose, and this is phi of x. So what we are indirectly doing, we are doing here, so what we are doing now here, oh sorry, okay, what we are doing now here, this is nothing but phi of x into phi of x prime. This is the dot product we are directly getting. This is the dot product what we are getting from this. And if you see in general, if I write what is phi of x, phi of x is the feature map which are mapping your low dimension data. Whatever low dimension you are having, this data you are projecting into the higher dimension. This low dimension, for example here to 6 dimension higher, and who is doing that? Who is helping you? Phi of x is helping you. So that phi of x which map your low dimension to the high dimension. So this phi of x, for example, consider this one as a comma b, okay. So this is nothing but your a square b square 1 here under root of 2ab, okay, under root of 2a and under root of 2b. If you put a equal to f1 and b equal to f2, you will get this data, like the whatever we got, f1 square f2 square 1 under root of 2 f1 f2 under root of 2 f1 and under root of 2 f2. That here these data you will get, these phi of x you will get, okay. And if you put g1 g2, you will get this data, phi of x, this value, okay. So whatever now we are now here saying that system, so what exactly now we understood from this is the important point. What we understood here, the x transpose x prime or x transpose x as of now plus 1, I am not taking prime here, see, this is a generic one. Okay, x transpose x plus 1 square, because this is what we took the example. Okay, this is a polynomial, like as of now it is like square terms. So this x transpose x plus 1 square computes the dot product, in transform space or in the higher dimension, because we are transforming the space from 2D to 6D. Okay, like we are, this is just example 2D to 6D. So we are transforming this space in transform space where, okay, the x transpose x plus 1 square that compute the dot product in transform space, because it's calculating the dot product, what you have seen now, the f, this is a dot product calculation. It is not doing x in x transpose x, it is doing phi of x transpose into x, and this is in what, in the transform space or the higher dimension, transform space or in a higher dimension, or in higher dimension. Okay, this is in higher dimensions. Okay, so this x transpose x plus 1 square that actually computes your dot product in the transform space where f1, I'm writing here, where where here f1 and f2, whatever your f1 f2 is mapped to, is get mapped, get mapped to what they got mapped to, f1 square, f2 square, 1 under root of 2, f1, f2 under root of 2, f1 and under root of 2, f2. These lower dimension things are mapped to higher dimensions, but we using what, phi of x. And what is that phi of x? This is the phi of x, x transpose x plus 1 whole square. So this is the function which map your f1 and f2 in lower dimension to the higher dimension. Similarly, same thing for g1 and g2, which is mapped to same way, g1 square, g2 square, 1 under root of 2, g1, g2 under root of 2, g1 under root of 2, g2. So these two, whatever these lower dimensions, whatever this lower dimensions x is there, whatever the lower dimension x, which is belongs to your R2 2 dimensions, is mapped to your higher dimensions in the R6 by using, like, this is mapped to higher dimension R6 by using your phi function, phi of x. Okay, so by using this phi function you are mapping the lower dimension x to phi of x by using this phi. Like I mentioned here, phi of x is nothing but your output, final output, which is in the higher dimensions. So x in the lower dimension of 2D is mapped to the higher dimensions, like a 60, like a small 2D is small here, 6D is capital. Okay, higher dimension 6 is by using this phi function. So this x is converted into the phi of x. Okay, so here we managed to compute this. So what is our aim? Why we calculate this? Why we use this x transpose x plus 1 whole square? So what was the reason behind that? The reason is, we saw that the reason is, we know that xi and xj is there, and we have to calculate phi of xi and phi of xj, and then use that and then calculate phi of xi transpose into phi of xj. That is what we thought this is the process. But the problem is, this calculation of phi of x and phi of j is dangerous. We can't do these operations here, we can't do. So what we decided, can we get another route to directly calculate this phi of x transpose into phi of xj, xi transpose xj? Yes, there is a route. How to get that? Use some phi function. What is that phi function? Okay, in this example, use x transpose x plus 1 raised to 2. Use this function directly. Xi and xj is transposed to directly, xi and xj will, this lower dimension is mapped to your higher dimensions, f1, f2, 1. So here we don't need to calculate your f1 phi of xi and phi of xj separately. Directly you are getting the dot product, because if you see here, this we are directly getting the dot product, f1 f21 is dot with sorry, here, yeah, here, this dot product, this is dot product with g1 g2. So directly you are getting this phi of x transpose phi of x hat of xj, or something like this way here, x prime. Okay, so I'm not now calculating phi of xi and phi of x prime separately. I'm directly calculating the dot product. How I'm calculating the dot product? By using this, by using this by using this example. This is one function which give me direct from xi to xj, direct this dot product. So no need to individual calculate phi of x. Directly you can calculate the phi of xi transpose into phi of xj directly. So this is the very important function. This is just one example I gave you. Okay, so this is just calculating the doing this one. So it is like a square example I gave you. So for example, if I take another examples, like there are more examples we can consider now, more examples. Okay, because you said x square is only possible, or can we go with xi, can we go with another cube or another power, is it possible or not? So what happened now, here we consider this function as whatever the function we got now, x transpose x plus 1 whole square. So we name them as a like x prime. Okay, we name them as a k of x comma x prime equal to x transpose x prime plus 1. Okay, instead of square we consider p. Okay, instead of square we consider p. So that what that x is belongs to rd, because you know that this is lower dimension rd, and here p is any value like 1 2 3 4 5 6 which is greater than 1, greater than or equal to 1. Okay, sorry, not equal to, greater than 1. If it is equal to, then it become like a linear relationship. So it should not be equal to, it should be maybe, yeah, greater than 1. So it may be 2 3 4 5 6, anything, any kind of any value, any value you can use. That power, 2's power, 3 power, 4 power can be a valid function. This can be a valid function. And how you can get the valid function? Like, because now we did it for our 2, when it is x transpose x prime plus 1 raised to 2. We did it just now, and then we got that phi transpose xi into phi of transpose sorry, x prime, and this x and x prime, we got that, and we understood that we are saying that it's a valid function. Valid function is what? Valid means in terms of this current situation, when there is a non-linearity, and we are saying we are using this function, and we are saying it should be a valid function. Valid function means what? Once you do the dot product in the higher dimension, phi transpose x into phi of x, that dot product is present. If it is present, you can calculate that, then you are saying that this is a valid function. So you have seen now the dot product, you whatever you have calculated, okay, that dot product, like the dot product is exist, that phi transpose x, every time write these, I should not. Okay, gone. Okay, it is phi transpose xi into phi of x prime. So if you able to calculate the dot product, I'm not saying calculating phi of xi separately. Okay, I'm not saying calculate this one or calculate this one. I am directly saying calculate the dot product. If you are able to calculate the dot product by using that function, like if you are able to calculate here in this term, if you are able to map this xi and xj to higher dimension without calculating this phi of x and phi of xj, by using some phi function, that what is that phi function? X transpose x plus 1 whole square, that here we took p equal to 2. If you are able to map this xi xj to the higher dimensions and calculate the dot product, that is a valid function. So if I consider that one as a p equal to 3, then you need to do the same calculation. If you do this p equal to 3, because what we did here, so it is like a it's like a 2. So the I use this equation like a plus b whole square. So this 2 equal here. So I use this equation a square plus 2ab plus b square. So if you say if it is like a cube, then you have to use same term. A plus b raised to cube is like a cube plus 3 a square b plus 3 ab square plus what is that, b cube, yeah, 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 correct, this one. Okay, this is the equation. Then you need to put the equation here and then derive this here whatever now f1 g1 plus f2 g2, okay, plus 1 raised to cube, and then get this, solve this one by one, step by step. You will get like the same way another feature function, like mapping function, feature mapping function, which may be having more dimensions. Like here, how many dimensions? 1 2 3 4 5 6. Here you got 6 dimensions. But if you calculate for cube, you will get more dimensions, maybe 8 values here. And you will get here d has a g, whatever the g is here, it is having more dimensions. You will still get the dot product, but with higher dimensions. Like if you increase the number of power from 2 to 3, your dimensions will also get increased. But it also show you it's a valid function. It also give you some kind of a dot product. Like this also give you the dot product of phi of x transpose into phi of x prime. It will give you the dot product. So always remember when you are mapping your lower dimension into the higher dimensions, without, because what exactly we want to do, your main intention is to get the best line, or your main intention is to get the w, which gives the directions where you are trying to project all the proxies on that line. Okay, w is fine in the lower dimension, you are happy to get the w. But in the higher dimension, what you do, because lower dimension, if it is a 2 dimension, you can able to, it's happy, you are able to get w. But in a higher dimension, 6 dimension, what you do, so you need to get w. What, how you get w, that is something like a covariance matrix you need to calculate, and then you calculate eigenvalue and eigenvector. What is the covariance matrix? It is x transpose x in 2 dimension. In a higher dimension, what is this? Phi of x transpose into phi of x. Okay, this is covariance matrix. Calculate the covariance matrix, get your eigenvector. That is what the final aim, what you want. That is the best line. You can say that is the best line. So for getting the best line, you have to do this in a higher dimension. I am not saying in the lower dimension. This is a higher dimension. That whatever the best line you will get, that is also in the higher dimension. Okay, whatever the best line you are getting, that is also in the higher dimension. That's not in the lower dimension. That line will also be in the 6 dimension, whatever example we have seen. And you now just saw that here what in the when I'm just projecting f1 f2, it is mapped to f1 square f2 square 1 this value, this here, like 6 values it's mapping, correct? It's like limited, it's like a vector. It is a vector with a 6 value, or you in Python term we can say that it's like a list with a 6 values. Okay, not more than 6. This 2D is mapped to 6. If I'm doing this for 3D, that will be some more than 6 values, something more than 6 value, 6 plus x something value. If you do fourth power mapping, it will be something more than this. Like what you need to do is same way, a plus b raised to 4, that you need to calculate. Okay, a plus b raised to 5, plus 1 raised to 4 here. Okay, plus 1, because our function is what, our function is x transpose x plus 1 raised to 4, raised to 2 raised to 3 raised to 4 raised to 5 raised to 6, something like that. Okay, so once you increase that, that dimensions will also increase. But if you see that they are limited, it's not infinite, they are limited. They are like 2 to 6 is fine, and if I'm doing 4 to 15 is fine. If I'm just projecting to the cubic relationship 4 to 15 that we have seen, it is very good. It's limited, it's finite. But there may be some another situation where we'll see the second example, because first example, in the first we saw the function is what, in the first example we saw the function will be x transpose x plus 1 raised to p. This is one example, one phi function or feature map function, which mapped your function to your higher dimensions for x comma x prime is same thing, x transpose x prime plus 1 raised to p, and p is greater than 1, and your x belongs to rd, like lower dimension data. Okay, what is the second example? The second example, this is the examples I am saying you. Okay, what will be the second example? The second example will be, this is important, okay, x comma x prime equal to exponential of minus x prime whole square divided by 2 sigma square. Okay, for some sigma, because you know that the sigma should not be there, for some sigma which should be greater than 0 or should not be equal to 0. Okay, should be greater than 0 or not equal to 0. So you know that this, what is this function? Did you guys have seen that in math or in statistics also, Gaussian distribution or like different distribution you have seen. So this is what, this is the Gaussian map, that function called as Gaussian map, sorry, Gaussian map, or it is actually the PDF. We know that PDF calculation, we have seen that stat. So it's a Gaussian PDF, or the important name what we are using in our next part of algorithm is radial basis function, or we simply say RBF. Okay, this is the radial basis function. Okay, and you can simply, like, now what I just showed you that how this phi of x transpose phi of x for the square, which one, x, if you see kernel means exponential, that's all. Whenever the kernel SVM comes, kernel PCA comes, they consider by default the Gaussian kernel only. So we have like two types of kernels. One is polynomial kernel, another is your Gaussian kernel. So polynomial kernel is what, the example one, what we have seen, that f1 this x1 square x plus 1 whole square. So instead of that we consider p x1. So here I have written now. Okay. So yeah. So this example, this is p. This is called as polynomial kernel. Okay. I don't want to give the name right now, but I said that, I thought, okay, you asked me. So polynomial kernel, this one called a polynomial, and this is what Gaussian kernel. So this is what the Gaussian map, Gaussian, like radial basis function we call, and this combinedly, these two examples whatever now I give you now, 1 and 2, this is called as your kernel functions, and that kernel functions give you the kernel PCA. But we are not finished yet, but I'm just giving you. Okay, so why we need this another function. Oh, sorry, I did not see. I'm sorry. Sorry, I did not see that. Ma'am, tell me question. Okay, ma'am. Basically, ma'am, because mostly we try to, if the question asks, because in the questions generally in the application we use the Gaussian kernel in the applications generally, and but in the question exam and all, if they ask like use the polynomial kernel, then you need to use this x transpose x plus 1, this kernel. Okay, you need to use x transpose x plus 1, this type of kernel. If they don't ask, then you need to use by default this exponential of minus of x minus x prime whole square divided by 2 sigma square, this kernel. Okay, and yeah, yeah. Okay, so these, because there will be different examples also, different kernels also, but in our case, we in our exam or in our syllabus we use two kernels as of now. this Gaussian kernel. Maybe they have done this kind of research, and they found that instead of calculating the phi of x and phi of j separately, you can directly map your phi of x, x and y to, you can directly map here. I just draw this diagram, no? So you can directly map, here, yeah, you can directly map xi and xj to this phi of xi and phi of xj. I have one example running demo. I can maybe show you that. It's the best time to show you the demo. 1 second, huh? Yeah. Okay, this is kernel PCA. This is something like a non-linear relationship graph. Okay, and I am calculating the actual kernel here. Compute RBF, like the radial basis kernel. So I'm using the radial basis kernel mostly, like by default. Like, I don't say by default, because I don't work more on that, but whenever I saw the examples, also the examples mostly use the this exponential or this Gaussian PDF or Gaussian map or radial basis function as a kernel. So they use this kernel here, and this kernel give something like this. This is the output of your, so your data was something like this blue and this orange color. And once you, this is non-linear data, this is a Moon's data set, and once you apply this kernel PCA on that, the data become like this now. After your kernel PCA, once you apply, it become like this. So it is showing some kind of like, it's now it's easy to differentiate between these two data set. You can put some straight line or some kind of inclined line here. So see here like this. So here what happened, I'm using SVM afterwards, and I'm then just putting this line which just separate out these two data set. So this is the SVM classifier I use, just to give the idea of what exactly is happening. So the circular data set is now becoming this kind of a data set, and what I did, I use this Gaussian kernel here you can see. So exponential of the gamma, because this Gaussian kernels need this sigma, whatever the under root of 2 sigma square, so that sigma value and this kind of operation. So I use the Gaussian kernel to just to make sure that this non-linear data will convert into the linear data, and once it become linear data, what I need, I just need to because PCA's work is done. PCA is now put all the data, non-linear data, into this like a linear kind of a data. Okay, it is not every time you will get like this output. Okay, if you, this is something like practically there are like some noises are there, so your data with some noise and having different kind of distributions, not exactly the circle, because it's not a circle. So if it is exactly circle, that is more accurate, like in lab and all, you can create this kind of a data which exactly having the circle. So this circular data here, it is having the circular data, and if I apply the PCA on that, the kernel PCA, it becomes like this. So it is not showing, it is not telling you that it become linear, but what PCA give you, the final output, PCA's final output is giving a directions, or giving the directions where the maximum variance is available. That's all. So PCA calculated the maximum variance, and he just created this kind of a graph. But this graph is very standard, which is exactly, if you see the exact data, it is become like a exact circle. But generally in normal application, the data comes with the lots of noise and everything. So this kind of a data you will get, and this data, if you do this PCA on that top of this, so you will finally get this is the output of your PCA. PCA is showing there are like a, this way it's showing that this data, this maybe the principal component of this side is the blue line showing more variance in this side, and your orange color is showing more variance in this side. So these are the two differentiated data, two different datas here, and it differentiated this, and you need to separate out the data by using your SVM classifier or any other classifier you can use it afterwards. Okay, in the downstream. But this is how we use, like with the normal like in normally I use this RBF kernel, like radial basis function, which Gaussian kernel there. But in kernel PCA, mostly, like not mostly, because I did not work more on that applications, but what I have seen is on internet and all, like the people use this RBF functions more in the kernel PCA. And how they derived is something like, they just thought, okay, let's see whether we can get the lower dimension x data from lower dimension to the higher dimension, like phi of x data, but without calculating your phi of x and phi of xj separately. You want the dot product, because dot product is what the coherence matrix, and the coherence matrix will finally give you some kind of a eigenvector or eigenvalues. So maybe you don't need the line there, drawing the line, but here I will come to the point, next points I will come, but I think because yeah, the generally as per my current information knowledge, mostly like the user kernel in kernel PC is the RBF function, radial basis function. And in your exam, if they will ask, then it is something like they will ask use the polynomial kernel or Gaussian kernel or radial basis function or RBF kernel or Gaussian map, something like this. These names will come. Then you need to choose which kernel you want to use at that point. But there is a difference between these two kernels, okay? That I am going to explain you. You did you see this? Okay. We will see once again this point, okay, but this is important because you are interested in just jumping from xi to xj to this dot product in the higher dimension. You are not interested in calculating fx and fxi and fxj, like phi of xi and phi of xj. You are not interested in calculating separately. You are interested in that dot directly the dot product. So you are mapping this lower dimension xi and xj to the higher dimension, this higher dimension dot product, by using some functions which are like the functions which is derived. There are so many functions, but in our course we consider that like these two functions as of now, polynomial kernel and your Gaussian or radial basis function kernel. So these functions, like you see, well, now we consider like x1 x transpose x prime plus 1 whole square, that I showed that this is showing you the phi of xi into phi of x prime or something, x and x prime, okay, not x but x into x prime, that I showed you. So means once I showed you, this is like a valid. Same way we can also like show this whether the exponential of minus xi, because whatever ma'am I mentioned you na, whatever the functions we are taking the functions and these kernels, once that kernels is showing you like minus of like whatever the functions I am taking, that functions are valid only if they give you the product of your phi of x transpose into phi of x in the higher dimension. If the product is available, then only you are considering that function. Otherwise, if it is not available, otherwise if you can't get that type of product in the higher dimension, then this function is you reject that function. You don't need to take that function. So the functions what we are now considering, these functions are like already we calculated, or like research happened there, and then they found that these are the few of the functions from the bigger list. Maybe they have on lots of list of the functions, but we are now learning only the two. One is polynomial, one is a Gaussian function, okay. And that's why these functions, because I already consider this as a one of the example, so we can also prove that whether it's a valid kernel or not, valid map, by using the same way like what we did for polynomial kernel, a plus like a plus b whole square, this formula. The same way you can like use these things and prove it. So that we are not proving now, but yeah, that we can prove also, and that shows that these are the valid functions, okay, valid functions. So but the problem is, what the point is, in the polynomial function, what happened in the oh sorry, I will just zoom it here. In the polynomial function, what happened, we know that when we are having 2-dimension data, you are projecting into the 6-dimension data. That's fine. 2-dimension is what, f1 f2. You are projecting to what, here you are projecting, sorry, okay, I'm just okay, now I'm able to draw it. My pen sometimes works, sometimes it's got hanged, I don't know. Okay, still okay, I think I will open the, okay, 1 second. I will open the new Microsoft, this one, because this is hanged. This, okay, so okay, what we do, maybe we need to take 2 minutes of break or 5 minutes of break. By the time I will open the new paper page of this notebook, and then we'll continue. So this is the coming things is important, because uh, okay, okay, wait, our break is now postponed it, so let's do that. So in 6D what happened, like we know now, f1 square, f2 square, 1, f1, f2, and then f1 and then f2. These are the 6 dimensions in 6D. Okay, these are the 6 dimensions. So we got that these two features in the lower dimension map to the 6 features. Okay, but what happening, this is something like a polynomial kernel, x transpose x plus 1 whole square, or 3 or 4. If I say 3 or 4, then you will get some kind of a one phi function or phi of x here, which has this kind of a data. Okay, this kind of data. But what will happen in this exponential or RBF, radial basis function, that is the point. Okay, in the radial basis functions you are mapping your lower dimension data to the infinite dimension space. This is the main thing in the exponential or your Gaussian map or your radial basis function. Whatever the things you are now having in this polynomial kernel, it's limited. It is like an array of 6. This is like a vector which is finite. Okay, finite vector. But in the RBF, radial basis function, or your Gaussian or exponential function, it is actually mapping your two-dimensional data in the space, in this unlimited infinite space. This is the point. You will say, what is the benefit of undoing this one? We will come to that point also, but this is something is important. This is the difference between your examples like polynomial kernel and your exponential kernel. So x is here, whatever x is here is mapped to your infinite dimension space in the your RBF, radial basis function, infinite dimension space. So what happened in what is this infinite dimension space? So because you found that this is x is like 6D, 2D to 6D with that power of 2, or if you take power of 3, this will be something greater than 6, it may be 8D or something. If it is power of 4, it may be 10D or 16D, but it is limited. Okay, for the polynomial function. But here what happened, it is unlimited, it's going bigger and bigger. So how you can say this one? So if you see the example of exponential, like normal exponential formula, if you see, it is actually what? It is actually n0 to infinity x raised to n factorial. And if I actually see x, for consider x is equal to 1 as of now. Okay, consider x is equal to 1. So what will happen? 1 upon 1 factorial, okay, sorry, 0 factorial first, plus 1 upon 1 factorial, plus 1 upon 2 factorial, plus 1 upon 3 factorial, and it's going on. Is okay, so this actually goes on. So this actually goes on. You can't stop it, because this is exponential formula. Normal formula of e raised to x is 0 to infinity x raised to n divided by n factorial. Okay, this is going on increasing. So whatever the input you are now passing. Oh, someone is asking question. Okay, I'm just trying to once again collect my pain, but yeah. Okay, we will take 5 minutes break, guys. So because let me open the new tab, and it will take maybe should we take a break or should we continue? I don't know. Then because I'm just trying to open the new one, new tab. Uh, so the part left is something maybe depends. It is something, now we are at the end of this week, but once I explain this point, then I will give you the steps of Gaussian kernels, and that's all. But there some tricks are there, so you need to be cautious, like how we are doing the Gaussian kernels then. Okay, then only yeah, at least 1 hour. Is it okay for you guys? Okay. So we will take the 5 minutes break, okay, and then we will come back after 5 minutes. Now it is, I think yesterday also we took the same time, two. So yeah, 5 minutes we'll take. Okay, man. Yeah, we'll see. Yep. Should we start now? Yeah, Murli, I can't hear you, but okay, okay. I thought you guys are like offline or so. Okay, okay. Let's now start the remaining part because this is we are almost 60% of our kernel PC. So what now we understood, I just actually cleaned or I just actually started with a new my note here. Okay, so that's why the earlier data is not here now. Yeah. Okay, 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 okay. But okay, but yeah, I try to write it properly because you saw that I'm just now if I'm okay, okay, okay. Yeah, yeah. Okay, then I will do that. I will also do that. That's good thing. Okay. So now our aim is what we have seen now, like whatever the points you are having, xi and xj, instead of calculating phi of xi and phi of xj, instead of calculating these, you are directly jumping to calculating phi transpose of xi into phi of xj. That's why. So you don't want to do this operation, you are directly dumping from here. So for doing this xi and xj, for doing this you need some kind of a map function which can just map your two-dimensional data or lower dimension data to higher dimension. Okay, so in this example it is some example we took two dimension f1 and f2, there may be higher dimensions also. So that low sorry that there may be more than two dimension also in the lower dimension. Okay, so that you are mapping to the higher dimension data. Okay, and that what in higher dimension you want to do, you want to calculate the phi of xi transpose into phi of xj. Okay, this is what you want to do. So once you get that, that is nothing but your covariance matrix k. Once you get the covariance matrix, you calculate the eigenvector and eigenvalue. That is what your final aim. Sometime your aim is like doing calculating like this, but in the higher dimension the picture comes little different. It's not like the normal get the line directly, it's not like this. So you are like considering now you are considering some kind of a functions that will come to that point what we need finally. But we are trying to get some functions phi which convert your xi and xj lower dimension data to a higher dimension dot product. Okay, the dot product in the higher dimension. So we are interested in the dot product only. Okay, dot product. Okay, this is what we interested. And we saw there are two kernels. One is your polynomial kernel, which is nothing but x transpose x prime plus 1, which is p should be p is greater than 1, which is like 2 3 4 5 6, and here x is belongs to rd. Okay, next kernel is what we have seen, that is the polynomial kernel or radial basis function. Okay, that kernel is something like a exponential of minus of x minus x prime whole square divided by 2 sigma square. Okay, and here sigma is greater than 0 we mentioned. Okay, sigma is greater than 0. Okay, this is what our requirement. Okay, this is second kernel, and we said that this rbf, this is called as rbf. Okay, this is I will write the name as, this is a polynomial kernel, and this is your rbf, like a radial basis function kernel, or we call this one also as a Gaussian kernel. Okay, Gaussian kernel. Okay, we know that whatever value we got it from the polynomial kernel, this is like this is a finite values, because you saw that 2D is now projected or mapped to the 6D. 6 value is the finite value. If 3D is mapped to some value, it is also finite value, it's not infinite. But in polynomial kernel, these values are not finite. It's actually projecting your lower dimension data, maybe 2D, 2D, 3D, 4D, whatever may be data. It is actually projecting that to the higher dimension in the infinite space. It's kind of an infinite data, or like it has infinite of data, and you are trying to get some data from that infinite data set. Okay, so I can represent, because I cannot say like, okay, this is a vector and having a square and b square and then something like it's not possible in the finite domain. Correct, it's not possible in the infinite domain, it's not possible. So how I can say, instead of writing like this is your lower dimension data, your lower dimension data, your lower dimensions data is mapped to some function, is mapped to some function. Okay, what is that function? For example, I am having one function. Okay, this is a function f. So you can take any value, this is the input to the function, whatever may be x1 x2, you will get the output value here. Like output is y1, for example. You can take x2, you will get y2. If you are having infinite inputs, because as we are now going to the infinite space, if you say like this, okay, if whatever may be the inputs you are having, it has that is the output for that, is respective output for that. Okay, if you are having x input, yn is the output. So whatever may be your input, it is this function is mapping that input to the corresponding output. So there is no limit. It is saying I don't have any limit. For earlier polynomial case, it's saying I have a limit. I am having f1 square, f2 square, f1, f2, and then f1 and then f2. I am having this one. But he is saying, no, I don't have any limit. Whatever input you give, I will give output. So it is saying that whatever the input you are having in the lower dimension, you are actually mapping it to the higher dimension. So that mapping this point to, instead of a higher dimension point or feature, it is mapping to the function. So in polynomial or Gaussian kernel, there is no something like this kind of f1, f2, f3 like this. It has some kind of a function, and this function is what we have seen now here. This is the function. Okay, this function, whatever the input you are giving, it put that inputs there and give you the output. That's all. So the output is not in any kind of a limits, like this kind of limit. This output is like depends upon the input you give, you get the output. So the polynomial function, the radial basis function kernel or the Gaussian kernel, this kernel is mapping your lower dimension input to the function in the higher dimension. Okay, this is the function in the higher dimension. Okay, and the dot product between this function become integral. Like we saw that in the earlier case, that our f1 f1 square, f2 square we got, and then we got our g1 here f2 square, like a g1 square, g2 square. What we are doing, we are doing some kind of a summation there. Correct. And the same way for this data point. Okay, for this data point, for this this pair, because I show you some example of this 1 2 3 4 5 6. There what we did, we just did a pair to pair matrix multiplication. 3 to 4 is one value, then 1 to 2 to 5 to 6 is another value. Correct. So we got this kind of a, we did this kind of a calculation. So you are just doing this value and then this value. So here these are the pair to pair dot product calculation. The same way we are doing, but here the same calculation, and here final operation is something like, in the polynomial case will be something like this. If I do the dot products and summation of all the dot products, then it will be summation something like this. But in the polynomial, in the Gaussian kernel, it will be integral. Phi of xi into phi of xj of t. Okay, 0 to infinity, because it's like going till infinity. You are adding all the values. What we have seen is like x e raised to x. How we can write it is something like n equal to 0 to infinity your xn divided by n factorial. Let's say x is like a x raised to 1 plus 1 factorial, sorry, 1 here because 0 factorial here, so divided by 1 factorial x upon sorry x, if I say x is equal to 1, because if I just need to do all these things like here also, 2 factorial and so on, it's still infinity. Means you are just adding everything now. See, this addition, this addition, this addition. So if you try to write these operations, then these kind of additions is going as a integral part, like this integral operation. You don't need to like think about that, because this is like infinite domain in the higher dimension in terms of the Gaussian kernel. So you don't think more into that, but these are the 2 points. What happened is these dot products in these kind of functions, dot products between these functions become integral, because these are the functions. So the dot product between these functions become integral here. Okay, just remember, because this is not something which you will like exactly using, but just remember, in infinite domain you are mapping your low dimension data to function, not the point. You are mapping the lower dimension 2D data or whatever may be the lower dimension data to some function in the higher dimension, and the dot product between the functions become the integral. Okay, so this is something like the Gaussian kernel. But now we are coming to the point. Okay, now we are coming to this point. So let me type it here, because whatever the two kernels whatever these kernels, whatever these 1 and 2 kernels I say mentioned you, these kernels are like valid kernels, and we can like prove that by using like by calculating the fx transpose of I into dot product into x prime, like x prime, not I but it's x and x prime. We can get that value, and you will say that okay, it's this is possible, this is coming, so these are the valid kernels. But is it like the correct way that you are saying that okay, if you just get the dot product and this is a valid? It is a correct way to get the validation of the kernels. So in general, okay, in general, how we can say it's a valid kernel or not? Now this part we'll see. In general, how we can say is it a valid kernel? Given function, whatever may be the function, like polynomial function or exponential function, in general a function k, okay, in general a function k with two d dimension data. Okay, in general function k with two, how many are here? Two, these two d dimension, okay, d dimension data, okay, d dimension data gives output as the real number. Okay, so what it is saying, how can we say that if this is a kernel function, how can we say that a kernel function which has two d-dimensional vectors or 2D-dimensional data, and that map to the some real number, how can we say that is it like the valid kernel? Because you saw that now in the exponential you are just like the function you are having here, function you are giving some input getting some output, so you are giving some input getting some output which is like a real number. And this k function you are saying giving input getting some output, and this input is actually rd cross rd, like a 2D dimensional data. Okay, you are giving this dimension and getting some output, and you are saying whether this kernel is a valid kernel or not. So there are two methods we can say that it is valid or not. So there are two methods whether this kernel is valid or not, that we can show it like this way. The first method that you have already seen, that the first method you have already seen, that method number 1. Okay, in method number 1 you already saw that, like if if we can calculate phi transpose of x into phi of x prime, if we calculate this one, if you calculate this value and you feel that okay, I can calculate the dot product in the higher dimension, so it's like a valid kernel. it's also okay, you can do that, it's not a problem. But it might be hard, like for example, because as I said you that I gave you the, like once you calculate the dot product, like phi transpose x I, phi transpose x into phi transpose x is available, is possible. Sometime what happen, the dot product is not possible in the higher dimension. Sometimes the dot product is not possible, so that kind of a dot product is not possible, that then this kind of function which map your xi. Yes, so for example, this is a higher dimension data, and you are just mapping that lower dimension to higher with some phi function, okay? And you are able to map means what? You are able to map means you are calculating the x into this one. Indirectly, you are doing this calculation. Like you are doing this calculation. And if this is possible, if you get this kind of a dot product operation, if you are able to do the dot product operation, then you will say this phi function is perfect, it's valid. If you are not able to do, because in earlier here what we have seen, this example here, what we have seen, like, yeah, here what we saw now here, see f1 f2 f3, you just did the square of this, and then you got this is phi of x transpose, here this phi of x transpose, and this is g, okay, this phi of x transpose into phi of x prime. So you got that, like you just calculated, you just you solve this equation, a plus b whole square, like this you solve it, and you found that these are nothing but the dot product of two f1 and g1, these functions, dot product of these two values, correct? You got that, so you got the expression, this f1 square g1 square plus f2 square, this is nothing but the dot product of two. So you said that, oh, this is like a valid function. But if there are some functions, like for example it is something like some different equation which is non-linear, like having some kind of a polynomials like 3 4 5 6 7, but it is not like xi transpose x plus 1, it is maybe something like different kind of equation. For example, you can say it is something x plus 2x square plus 3x cube plus 4x minus 1 whole square raised to 4. Is it like a valid kernel or not? And if I want to derive this what exactly it wants, then I'm not getting something like finally this kind of a dot operation. I may get some equation like x in x square plus like f1 square plus f2, and so much equation, I bigger equation I get, but I'm not able to separate out f and g here from this equation, okay? So I'm not able to separate out f and like g, whatever the example we saw. So this was the easy one, that's why we are able to separate out this here, it's easy one, so we able to separate out f1 f2 1 and this and g1. But some calculations or some kind of kernels or some kind of functions will be there where this f and g cannot be separated out, that you cannot show that as a dot product, okay? So that type of kernels are not the valid kernels, okay? So this is something, because this is not every time that you do this some calculation and you are able to separate out the f and g from the calculation. And if you are not able to separate out this calculation, then your kernel is not a valid kernel, okay? This is not your valid kernel. So yeah, is it did I answer your question or still you are having question? Yeah, yeah, I will tell you, one second, huh? Let me clear the things. So what happened, like in our earlier example, what this example I have, I will just show you this f1 g1 square f2 g2 square, okay? So in this one, maybe I will write down this one here also. Let me write, okay, f1 f1 square g1 square f2 square g2 square 2 f1 f1 f2 g1 g2 plus 2 f1 what is that 2 f1 g1 2 f2 g2, okay, 2 f1 g1 and 2 f2 g2. So you found that if you do x transpose x plus 1, okay, whole square, And what x we consider? X is what? Your f1 f2 and x prime, and x prime is what? Your g1 g2. And we put that f1 and f2 in this one, and we just did that, and we found, we put this x and x transpose here, we do this plus 1 and then square, we found that this is the equation. And how we then we separate out this f1 square, then f2 square, under root of 2 f1 f2, and then under root of 2 f1, and then under root of 2 f2, and then 1, because this is the constant. Okay, did I miss the constant here? Yeah, this constant I have, okay, this constant here, plus 1, I need to write plus 1 also. Okay, so this is not the, this is the way, not the square bracket. Okay, so I am now separating out this. So same way here, if I just do g1 square g2 square under root of 2 g1 g2 under root of 2 g1 under root of 2 g2 and 1. So if I just do this, this is called as phi of, this is consider, this is phi of x, and what this is phi of x prime. Okay, because this x prime is nothing but what? G1, x is like f1 f2, so this one. Okay, so if I do phi transpose of x into phi of x prime, if I just do the dot product, if I do the dot product, what I will get? The dot product, I will get this line, this value, correct? If I just do f1, you know that, correct? This is like how much? This is one row, 1 2 3 4 5 6, one row 6 column, and this is what? 6 row 1 column. Okay, so I will get finally one value, 1 comma 1. So the output will be something like 1 comma 1, correct? Some number, correct? Some value I will get. So this transpose, whatever I am doing, this transpose give me, if I do like, you understood me here, ma'am, what I am trying to say? Yeah, so here some equation I am able to, if I just do dot product of this phi transpose x and phi transpose x prime, I am getting this equation back. And for example, if I am having something different now I am having something like a 3 by 2 f3, something like, there is no f3 here, but for example, if I am having f3, okay, f3 cube. Okay, so can I do now here? I can't do this, I cannot differentiate now, I cannot add something f3 here, or like these are the two terms, but there will be like a different equation, like 6 of f4, because if you are increasing the number of feature, because now we consider it just a 2D. So if I want to bring it to 3 dimension, if I bring it to 3 dimension, like f1 f2 f3, then this, and then I will do x transpose x plus 1 cube, then these equations will be very bigger one, and that I can do. But if there is something different equation, if there is something like a different equation, like maybe not this one, because these are valid kernels, but if there is something different equation, okay, then I cannot, maybe in this scenario I cannot like separate out f1 f2. If I separate out, still this column is something different, and if I just multiply this phi transpose x into x like this, that will not become this value. This is not the, this answer of this won't be here, something like this, whatever now new one is here. So that is not equal to, so phi transpose x is equal to phi transpose x prime is not equal to your this answer, whatever the bigger answer you are having, this bigger equation. Okay, so that time this is not valid kernel, this is not the valid kernel, that has to equal to, that has to come equal to. Okay, if that comes, or this dot product exists, this dot product is present. How you say dot product is present? Because in this case you know that when I do the multiplication of this, I am perfectly getting this value back, I am getting this value back, means this is perfect valid kernel. But if I don't get the value back, this whatever equation you are having, if you don't get the value back, means the dot product is not available, means the dot product whatever you are getting is not the correct one, means you are not having the proper kernel there. So this kernel is not the correct kernel that you will use to map your lower dimension data to the higher dimension. So the valid kernel whatever is here, So the valid kernel is something which you get the phi transpose x. So this method, with this method, if you get this phi transpose x into phi transpose x prime, if this dot product is available, means here this example here, in this example, if this dot product is available exactly, then only this is a valid kernel. But the problem is what here, because it's a 2-dimensional data, so it's I'm able to do it. But if it is 3-dimensional data, it will increase this vector will be more increase, and then this g will be more bigger one. Okay, so that will increase. So that will actually what, this is very hard time to difficult this kind of multiplication, like dot product is available but it is little hard time. So can we use another method? Yes, we can use the other method to validate whether the kernel is valid or not. So this method number 2 is now here. Okay, this method number 2 is now here. We found that like in method 1 it's okay, you got this xi transport, it's okay, like with a small 2-dimensional data with a 6D you are projecting, it's okay, then you got this phi transpose xi and all, it's very fantastic what you did. But if it's the data is more, it's also good that you can possibly get the data, it's not a problem, but it's little hard. So why should go with this method 1 if we have another option? So that another method is called as Mercer's theorem. Okay, Mercer's, Mercer's theorem. Okay, so you don't need to like go deep into that Mercer's theorem, you just need to know like what is the Mercer's theorem. Because in class also in the lectures also sir has just not gone into deep into that, but he just gives some informal way of like information about this. Okay, informal way he just explain you what is that Mercer's theorem. Okay, so what Mercer's theorem is saying that there is a function called as k, okay, which mapped your 2D-dimensional data to a normal number. Okay, because kernel, what I just showed you, that this 1 cross 1, whatever the 1 cross 1 you got, this is the output of your phi transpose x into phi of x prime. So this is just a one normal value. Okay, that kernel is giving you the normal the real number value. Okay, so we are now checking that in Mercer's theorem whether this kernel which map your 2 d-dimensional vector of d-dimensional data to a real number, whether this kernel is valid or not, and if it is valid, when it will be valid, if and only if the kernel is valid when as per the Mercer's theorem the kernel k is valid when k is symmetric. Okay, when k is symmetric means what, k of x comma x transpose, whatever we were doing, is nothing but k of x transpose comma x. Okay, just remember, just think like this one, because there will be different yes, we don't have any issue. If it is symmetric you will say yes this, but there is another point. Once there is like a, the method 2 says, Mercer's theorem say, if the kernel say that it's symmetric, then it's a like a valid kernel. But there is another point. What is the next point that we will see? The next point is, the second condition is for any data set, okay, for any data set which is something like we have like x1 till xn, where k is belongs to this Rn cross n. Okay, here k of I comma j, like you know that because instead of calculating the bigger matrix, we found that we can calculate the k of 1 comma 2, where x transpose 1 and x of 2, like this, like these pairwise dot product calculation. So like this I am saying here. So I am having xij, so I am whatever the kernel I am having k, okay, the kernel whatever I am having, I am putting this xi value and then xj value, and then I am trying to figure out whether this is also be a symmetry. Okay, this also should be a symmetry. not only k, this complete k should be symmetric, plus your this value has to be also symmetric. Okay, if this is present, if this is present, because see k is already symmetric, so from that we can say that from the, because from here we already found that k is symmetric, so from that we can say here this is also kij is also, like you can like derive it, but I'm not going into derivation, so I'm just directly writing kij is also a symmetric matrix, as we have seen in the, because we have derived here already, because what is this, k is equal to x comma x transpose, what is this, phi of x comma phi of x prime. Okay, and you just need to check that whether this, whether your equation x into phi of x is the same or not. If they are same, then you will say that these two will also be the same. Okay, if you able to solve this one, then you will also get the, you will also say that these are the symmetric. Okay, k upon this x prime and this also symmetric. So no need to like I'm not going to that complete derivation, which is also like not there, but you just need to know these are the compulsory conditions. Okay, these are like not one or two corrections, these are like compulsory conditions. Okay, the Mercer's theorem state that here whatever the your k kernel you are taking, if that kernel is symmetric kernel, then it's like a valid kernel. Plus there is one more condition, for any data set x1 to xn. Okay, then if you calculate kij this value, and that value the same, whatever the value you have calculated, the same value, if you put the same value in xi and xj, okay, in the kernel, the value whatever you are getting, okay, you should get some for same value whatever the xij what you are got. Like we saw that 1 2, we got the 1 2 value, and we also know that from the bigger matrix we know the first row second column this value. If both are same values, then this kernel is the perfectly valid kernel. Okay, so these are the two important things, like theoretically you should know that. Okay, theoretically this is important, it's not something calculations or something you have to do, but theoretically you should know that what is Mercer theorem. It's not like in the class also, it's not detailed explanation, it's just two statements you should know, like k should be symmetric, and whatever the kij you are getting, that kij value should also be the symmetric value. This is like a symmetric matrix, as we have already, this should be the symmetric matrix, where finally whatever you are getting, this should be a symmetric matrix, kij should be is also symmetric matrix. Okay, so because it's already the symmetric matrix, and we know that like symmetric matrix what, this symmetric matrix means what, once you get the kij means what, the covariance matrix. So what covariance matrix gives, this gives here variance, the variance which is like having maximum variance in one direction. Variance is also a positive quantity, correct? Variance is never be negative, so variance is a positive quantity. So variance is something positive, means from the variance you are able to get the eigenvalues, like eigenvalue is nothing but the variance, so the eigenvalues are also positive, eigenvalue is also positive value. So once the eigenvalue is positive, either the eigenvalue is 0 or it's a positive. If it is 0 or positive, what is kij matrix? Kij matrix is what? It's a semi-definite matrix. Okay, okay, so all eigenvalues of the k are like non-negative values, these are not negative values. All eigenvalues of the kij matrix is the semi-definite, or like non-negative means 0 or positive values. Okay, so kij has to be the kernel has to be symmetric, and kij matrix, whatever the kij matrix we calculate here, okay, this matrix, whatever matrix we have calculated, this matrix also has to be symmetric with the eigenvalues non-negative, which is like greater than 0. That matrix has to be semi-definite matrix. Okay, these three things you should know to say that whether the given kernel is valid kernel or not. If like whatever the kernel we have seen, the polynomial and Gaussian kernel, they are definitely passing these two conditions, that's why they are valid. So in future if you are getting some another kernel, you have to figure out whether it's a symmetric kernel or not. If it is symmetric, and then if you get the data from that, like x1 to xn data you are having, and you just calculate this kij, this matrix kij matrix, by putting the xi and xj value into that kernel function, and you get all the kij, and you created the matrix here, and you figure out whether this is like a semi-definite matrix and their eigenvalues are like non-negative values, and whether it's like a symmetric or not. Once you say that it's a symmetric, then you will say that okay, the kernel is the new function, or the new function whatever you suggested as a kernel is valid. Okay, so this is what all about the thing about the lecture 2.4, and now the final short sections is remaining, which is like the actual algorithm we are now going to write now here. So if you have any question till now, we'll take that, or we'll go proceed to the next part. But this is lecture 2.4. Okay, any questions, or we'll go to the next part if you are not having any questions, so we can finish this one. Okay, ma'am, semi-definite matrix means any matrix, for example, you are having, okay, a b c d. Like I'm taking a b c d, you what you do, you calculate the eigenvalues, you know that how to calculate eigenvalues, correct? You calculate the eigenvalues, okay, like you calculate the covariance matrix x transpose x. This is covariance matrix, and from the covariance matrix is nothing but what, c a minus lambda I, that is what your determinant, you get it, and then you get the eigenvalues, correct, eigenvalues. And if the eigenvalues what you have calculated, that eigenvalues is not negative, is all are positive or 0, okay, all are positive or 0, then the given covariance matrix, or the given matrix from where you got this one, so that matrix is the semi-definite matrix. Definite matrix means what, your eigenvalues are always be positive, like it's not 0, it's always be positive, and not like not definite means they are having like a negative values and all, but that's different one. Okay, but positive means, only positive means definite, and semi definite means they are having 0 value also, eigenvalues are also 0, they don't be like only positive, they will be 0 also, so that is like a semi definite matrix. Okay, okay, no problem. Okay, no problem. So this is something the conditions, okay, the conditions you should know. K should be symmetric, the kernel, whatever kernel you are, somebody comes and say you use this kernel, you can say that, wait, let me say that whether it's a valid kernel or not. So he will say, how you will say, then you can give the first method as yeah, I can just try to get my phi transpose x method 1 in this is the, I can either get this value phi transpose x into phi transpose, if this dot product exists, means I can say it's a valid kernel. Or method number 2, then he will ask, okay, what is the OR, then OR method is your Mercer's theorem. Okay, so we are not going deep into that, so we just mentioned that there were points which we need to take care here. So first, as per the Mercer's theorem, what Mercer's theorem say, that if point number 1, that is if the kernel is taking like the kernel with 2D dimension data is giving you the final real number, so with that k kernel is, if it is symmetric, if that kernel is symmetric, yes, it's symmetric. What is the next point? And that kernel, if you see that, if you get the matrix Kij by putting xi and xj value into that kernel, and if you figure out the Kij whatever you got, if that matrix is also symmetric matrix and semi-definite matrix, then after saying that 1 and 2 is pass, you will say that this is a valid kernel, whatever this will come, this is a valid kernel by using the Mercer's theorem. Okay, so now we are going to write our actual algorithm in the kernel PCA. Okay, but there is some tricks. Okay, here the point you need to understand, okay, properly. So the point is, okay, now we are going to write the video number 2.5. okay, so video, okay, so what we are now say, trying to write this algorithm for kernel PCA. Now we are writing, Okay, first point, okay, your first input, whatever input you are getting, the data set, same way in PCA you are having some data set. Okay, it's a PCA only, but it's kernel PCA because of non-linear data sets are there, that's why. Okay, x1, x2 and so on till xn. Okay, where x belongs to your RD. Okay, and not only this one, you are also having another one data, because in PCA you are having data, you calculate mean of the data, you center the data, everything you have done, it's very good, you did everything fantastic, but that's not a problem. Here in kernel PCA, along with that data, you are also having one information, that is what, that is your kernel. So the kernel function is also given to you when you are doing kernel PCA calculation. So what this kernel PCA kernel function is having, C2 d-dimensional inputs, okay, which give you some real number R. Okay, so what is the d-dimension? This is something like what I mentioned, f of x and f of x prime, this, and what it gives you some number, the product, this product gives something like that, 2D dimensional. Okay, so that's why this. Okay, so here in the step 1, so you are now getting two input, you are now getting two values, one is your input value and one is your kernel k as a input to your kernel PCA. Okay, then here you are now following one by one step. Step number 1, what you do in the step number 1, you are having kernel k, you are having kernel k which is of, okay, like same way I'm just typing for a second here, RD, which give you R. Okay, and you are calculating Kij by putting xi comma xj. You are calculating a matrix, this is your matrix. Okay, this is a matrix, and you know that this is a valid kernel, you already understood this is a valid kernel, that's why they have given you. So that's valid kernel, you calculated the Kij matrix. Once you get the Kij matrix, I will say this one as a K centered. Okay, because sorry, not K centered, it's like a Kij matrix. And what is the next step, what we need to do, you know that, like once you get the input data, once you get the input, what we do, we calculate the mean of the data and then center the data, x minus mu we were doing in normal PCA. Normal PCA we used to do that, but here we are doing the centering of the operation, centering the data. This is something different. Okay, this is not same as what we do in the normal thing. Okay, so because we saw that, and in our lecture also sir has, yes, yes, but what in lower dimensions, you know that center is easy na, because what is this data is somewhere here, correct, this data is here, and you are getting center, this is okay in lower dimension, but it's not like a straightforward in the higher dimensions. In higher dimensions you are now having lots of eigen value, like lots of feature values, not eigen values, sorry. So you are having in higher dimensions that just f1 and f2 here in lower dimension, you are now projecting into the 6 values. Okay, in Gaussian it is infinite, in Gaussian it is infinite, and that is also following the equation, like the function exponential of minus x into x prime whole square divided by 2 sigma square, it is following that function. Okay, and that function you are following, that is a kernel, and you need to center the data, means what, you are actually centering the data. It's something relatively it is little difficult in this case. Okay, so what it is doing actually, if I just actually if I just follow the steps, what we are having it, like you are having the data is x1, x2, xn, this is the data. So what we do, we project the data and get it, phi of x1, phi of x2, phi of xn. Okay, we get the data, we are just projecting the data, getting the data, correct. And what is next step, you are getting phi of x1 minus mu, then means like what, we are just subtracting the center, x2 minus mu, this is what, phi of xn minus mu. Okay, and what is mu? Mu is what? Mu is what? 1 over n summation of phi of xi I to 1 to n. Okay, this is fine. This is okay when it is linear data, when you are in the lower dimension and all. But now you projected the data to higher dimension, and now the phi of x comes once again here. Once again the phi of x is coming here. And why we are doing that much of like we are breaking our head from last 2-3 hours, and we are saying that I don't want phi of x, I just want phi of x transpose phi of x prime. Because phi of x, if you want to do, you know that phi of x, if you want to do, then there is a complexity of d raised to p. Correct, there is a complexity of d raised to p, and then I don't want to do that. That's the reason I actually went to this option. Like, why don't you go with that? Because this is complexity d raised to p, I don't want to do that, so I actually go with this dot product operation instead of going with the instead of going calculating phi of x. And in the centering operation, it's showing that just calculate phi of x and then minus the mean value, and mean value has the same phi of x. And it is like a doing, well, it's like a doing the same thing, like going into the same point where we don't want to go, like where we just try to avoid that. This is the main thing. So the entire this kernel, whatever the operations we are now having, so we have to figure out some another way to center the data, not with how we are like earlier trying to do that. Okay, so here, because we are trying to get the phi of x, but there should be some type of equation which will be in the form of this. Okay, there should be some type of equation which will be, this is what, this is the kernel. Okay, there should be some type of equation which is a form of this phi transpose x and into the dot product of phi of x prime. There should be this type of equation to get a value of mean, or to get your some value, so you can do the centering of the data. You don't want to just simply take this equation, normal equation, whatever now I just wrote, this equation, this, you don't want to take that equation now. You don't want to take that equation. You want to take the equation in terms of phi transpose x into x, because you know that I don't want to do calculation of this individually, this value. Instead of that, what I will do, because this is my aim, is this, my aim is this calculation, so I will not do this, I will simply go with this. So I am using this phi transpose x into phi transpose, and I am trying to convert the values or parameters in such a way that they looks like this kind of parameters, and that will be easy for me to center the data. Okay, so if I try to do the centering of the data, in the class sir has not given complete information, so this is something I am trying to give. Yeah, okay, see, centering the data, normally we know that get the data, calculate the mean, subtract the mean, you get the center data. Correct, this is normal lower dimension, you do that. Okay, but if you go to the higher dimension, phi of x, phi of x is okay, you are like here, now we are here. Okay, you are getting phi of x1, x2, x3, xn, then you are just subtracting that my mean from the phi of x1, phi of x2, and that's all. So this is like, you means you will say that this is center data on paper. I am saying center data on paper, you will be very much happy that sir I have finished my centering of the data in the higher dimension. Okay, this is not lower dimension, it's higher dimension. Okay, and in exponential function, higher dimension is like a infinite. Okay, these are the infinite. So in the infinite, do you want to do this kind of all the infinity operations like calculation and all, or you, and in that next point is there is a phi of function also, and we saw that phi of functions is what, phi of function, this phi of x function is having the complexity of like I have mentioned you know, if you are having 10 dimension and you are trying to project the data with the 15th power. Correct, so this will be 10 raised to 15. So this is like too hard to get the phi function, because that will only give you the phi function, that many that many dimensions, like you need to get that much big vector arrays, and that array will be like really difficult to get the phi. So you don't want this way to get the phi. And why you want phi function? Because you want to derive some kind of eigenvectors in the higher dimension. Like what you want to do? You want to do this. You want to do this. This is your ultimate goal. So to get the ultimate goal, you don't want individually phi of x and phi of x transpose. You don't want to do. You just get this complete dot product with some way. But when you are doing the centering, it is saying that use phi of x individual, phi of x1, x2 individual, and then subtract it from mean. But that is dangerous. You don't want to do that because you don't want to come back to the calculation of phi of x individually. You don't want to do. So in some way you are trying to get this subtraction, like whatever mean you are having, that you want to convert that mean. This is like normal mean, what you say, this one, this is like a normal mean you generally do, but you don't want to do in this case. Now in the higher dimension you don't want to do, so you want to convert this normal mean in such a way that the operation looks like this. The operation term will have this type of a term. The operation, or this is the formula of mu will have some kind of k term, because k is what? Phi transpose x into phi transpose x prime. If you have this term, then you can do that centering the data. That's what you want to do it here in the centering the data. Okay, so these operations I am just now giving you. K of I comma j. Okay, so this center, c for center. Okay, I am just now creating this matrix now here. Okay, so what is this? This is like your kernel something. Your kernel is what? Phi transpose x into phi of x prime. This is your dot product kernel. Okay, this is your dot product kernel. So what I am doing is now here I am doing it phi of x, okay, minus for example I will write xi, because here I mention ing. Phi of x, for example, if I write here this one, because I am just right now doing this operation. Okay, this operation I am doing, this operation I am just writing here phi of x, xi here, and this is xj minus mu is mean. Okay, and if I do this calculation, this gives me the equation of, I'm just writing the equation, xi transpose phi of xj minus phi of xi xi transpose into mu minus mu into phi sorry, mu transpose here xj plus mu transpose mu. Okay, this is what, just I just solve the equation here. This is the what, this is the equation, dot product. Okay, this is the kernel k. I'm just centering that kernel. Okay, that's why I put centered, that's why I put minus mu. But the point is now here, you know that what is this, you know, this is what, this is your the first term is your kij, the complete kernel kij. Okay, the original kernel. Okay, and what is this? This is one term, this is one term, and this is one term. Okay, so first here, number one, the first term phi of xi transpose into phi of xj, I will write this one as it is. It's a kij kernel. Okay, it's a original kernel. Okay, original kernel matrix. Okay, whatever you got it. Okay, original kernel matrix. Okay, next is what? Next is your phi transpose xi into u, like your mean, we say that phi transpose. I am actually trying to derive this equation. Okay, and mean is what? Mean is what? 1 over n, your all number from k equal to 1 to n, phi of your if you are having for example k values, like I values, k values, so I put k here. So this is what? 1 over n. Okay, I am just putting this one inside, which is k equal to 1 to n. Okay, which is nothing but here phi of, I putting this phi transpose xi because this is xy into phi of this xk here. Okay, so what is this? This is what? This is the, this is nothing but, if you write in terms of a k, this is nothing but k equal to 1 to n. This is what? This is one type of a k kernel, but what, this kernel is showing one row and here, because this I is not affecting this, this loop is for k and here. So what is this? This is nothing but, I'll write in another color here, this is nothing but average of ith row of k matrix. So whatever you are having this matrix k, you are going to that ith row and you are just calculating the average of all the terms you are having. Okay, so that is the average of this, and I am denoting this one as, I am denoting this one as a okay, now it's back, it's good. So I am denoting, oh no, so I am denoting this one as a theta I. I will write my, by using my mouse here. This is actually theta of I. Okay, is this back? Okay, good. It is theta of I. Okay, my pen is back now here. Good. Okay. Similarly, this third term was third term here. This is the third term, u transpose phi of xj. Okay, u transpose, or I will write phi of xj into u transpose. Okay, and you know that, like what is like, if you get that this value u is what, 1 over n, like same way I am just writing in this way. So it's like a summation of k equal to 1 to n. Okay, u is what, u I am just writing here. Okay, maybe okay, u transpose xj, this third. Okay, u is what, this is the u of x of k. Okay, which is a transpose k equal to 1 to n into phi of x j. This is nothing but 1 over n. Okay, so the same way how you got it now here, this, so you just combine them together and you found that this is average of ith row of k matrix. Same way this will come as, okay, k of j. Okay, this is the average of jth column of k. Okay, this is nothing but average of your, the average of jth column of k. This is the average of jth column of k, and the last term, whatever now you are getting, the last term is nothing but your u transpose, like mean square is just like a mean square. But if you actually do the calculation, like I'm just writing the directly the final one, so it is n square, like number of equations and you are having, and it is actually l comma k. You will say what is l and what is k. I'll just need to yeah, this is what I'm doing is like mu transpose and mu, this is like a different values, so it's something like 1 over n. So this is k equal to 1 to n phi of x of k transpose, okay, mu transpose mu into 1 over n. This is going from this is going from, instead of k, is going from L 1 to n phi of xl. Okay, this mu into mu transpose. So this is here and this is here. So you are doing the dot product. So once I just calculate this, and then finally this looks like here. Mu transpose here, this value. So this is the equation. And how we, so this is the average of all the elements. So whatever the elements you are having now, this element a, b, c, d, e, f, g, h, all. So if you calculate the average of all the elements, this is the average of all the element in the entire K matrix. Okay, this is the average of all elements in the entire matrix K. Okay, okay. So if you like, you don't need to like just I gave the idea, but you don't need to like write the complete things. So if you are having something like the final centered matrix K ij is nothing but your actual, because the first point, the first is what, actual K ij. So what is now I am having here, this, so this value. Okay, so I am replacing this one by K ij here. So I will write down at the end now K ij, this is your given matrix, the given kernel, and then your theta, because I mentioned that average of the ith row, whatever I have mentioned this point. So it is something like here theta of, 1 second, let me, whatever the sir has written, I'm just using that same for here, theta of I. Okay, and this is 1, this 1 is like n cross n, and it is having one value where it is having the 1 when there is like a j, whatever, 1 of 4, like if you mention 4, so this is like 4 cross 4, 2 3 4, 1 2 3 4 divided by the n, so it should like a 4. So like this is what the 1 in the function 1. Okay, so minus same way this 1. Okay, but here it's not transpose, here it is something I. Okay, it is theta because it's here this third value here, this value, average of jth column K. Okay, that is written as like here theta of j. Okay, so I'm taking this theta value here, theta of j. Okay, sorry, this is here, multiply transpose, this is first one, this is 1, and this last term is what you are now having. So we consider this one as a P. See this average whatever you are getting, so I am writing this one as a P, this one as a theta j, and here this one as a, maybe I'll just, okay, this one as a theta I. Okay, theta I, theta j, and then P. So P is a, this is what the P, so this is a P. Okay, so this is a P which has also the same this function indication, the function I, this is what I. Okay, the function n 1 of n. Okay, if you are getting is a 4 cross 4 means this is the function, all parameters are, all values are 1. Okay, all values are 1 because this is function 1, but divided by this, how, what is that, this is a 4 cross 4 means n is equal to what, 4, so divided by n, so that is 4. So you have to multiply everything by 1 by 4, something like this. Okay, so here, and this is what, x of j transpose. So this is the way how you need to do centering of the your data set. And don't worry, this in exam and all, that's not something will come. like in our normal exam, because this is something you just need to know when you are like doing actually the implementation. Because if you see in this my algorithm which I just showed you here in this example here. Yes, yes. So here center the kernel, see I am using this one. Your I just mentioned k minus that one, because you are doing the dot product here. So I'll just open this here, this k into this one. Okay, the dot product, like maybe I will write here one here. These are the dot products, okay, inside. So you are doing the dot product of one and this theta I. Theta is what? Theta I is this value, theta I. Theta j is what? Theta j is this value. What is this value? This theta I is average of ith row of k matrix, average of jth column of k matrix. Okay, and p is what? P is nothing but your u transpose u, which is like u square, like mean square. And mean square, earlier mean square has this phi, but now we don't have this phi. We are having this k, like a kernel k. So which is like a kernel, you know that like kernel is like phi transpose x into phi of x. That is like a kernel. So that you can easily calculate. There is no phi here, no, just phi operation. It's like a phi transpose into phi. So that's easy for you to use that trick instead of calculating phi separately. So you can use this centering of the kernel. Okay, the first step was the first step when we started writing the algorithm, the first step was I'm in the correct place, correct? Yeah, step 1, you get the input, you calculate the your matrix k. You get the input, you calculate the matrix k. Okay, means like k matrix is whatever your kernel matrix. You need to, you got the formulas and then you have to calculate the kernel matrix. Okay, you get the input, you calculate the k. And the next next point I just mentioned you calculate the center that k matrix. So whatever the k you are having, this k, okay, whatever the k ij you are having, that you use that and you center this. Okay, you centered this value. And how you can center? You can directly use this formula here. This is the centering of the point. Okay, this is what this step number 2. Step number 2, centering of higher dimension data. Okay, it's not lower dimension, okay, higher dimension. In the higher dimension, you don't know in infinite dimension also, because there is not if it's a polynomial kernel it's a finite, but if it is a non if it's a Gaussian kernel it's infinite. So you don't know how many points you need to calculate, because there is a mean calculation. Mean means sum of all, and if it is infinite, how you can do the sum? Sum of infinite, you can't do that. So in that case you have to use this kind of a trick and convert it into the kernel. What is the kernel? Kernel is mapping to some function, and use that, and you can use the function and calculate the mean there. And this is the way how you can calculate the centering of the data. The third point, once you calculate the center of the data, okay, once you get the centered k, this is the centered data, data. And what generally we do, once you center the data, okay, once you center the data, you compute the because this is something now the covariance matrix for you. Okay, this is because this center data is something like a covariance matrix for you. And you calculate step number 3, calculate the eigenvalues and eigenvectors. Here step number 3, this is step 2. Step 3, compute eigenvectors. What is that eigenvectors? We know that beta 1, yesterday's class we know that, we saw that beta 1, beta 2, beta 3 till beta L. And eigen values, what is that algorithm? N lambda 1 greater than n lambda 2, n lambda 3, n lambda L. These are your eigenvalues and eigenvectors. Okay, once you get that values, these beta values, you know that alpha is what? Alpha, like I will write yeah, instead of writing k, I am writing now u here, just to not to confuse with this k matrix here. This k number will be same then. So k, alpha u is what? Beta u divided by n lambda u. Okay, this is what you got, the alpha. This is what the eigenvectors. But what was the next step? Generally we know that in the issue 1 we saw that next step. Okay, in this step number 4, what you do? Step 4, you calculate the w. How you calculate w? You know that, like we know that k into, you calculate like the x into alpha x k. Like what is x? This x is your data points. You multiply the data points, you got w. Correct? You got the w because you just multiplied the data points there. Okay, but in the higher dimension, this x become what? Phi of x into what? Alpha k. Phi of x into alpha k. But once again, we are trying to avoid to calculating phi of x, and once again this phi of x comes here. You are actually trying to find out wk, which is the thing what you want to do in the PCA, general PCA, like get the lines and all. But still this phi of x is like coming here, so this is not at all allowed to get the phi of x. So this step is not allowed. Maybe I'll write in red color, you will see, not allowed. Okay, to compute phi of x. It's not at all allowed. You are not allowed to calculate phi of x. Okay, you say that phi of x is not allowed, then wk, I am not able to do that wk. Okay, if I do this one, if you say no, I want wk, but this, if I calculate this wk, this wk calculation defeat the purpose of, okay, defeat the purpose of whatever the calculation of, purpose of getting kernel calculation and all. Okay, calculation. And why this is happening? Because we are calculating because it needs phi of x calculation. I don't want to do that phi of x, that's why this is like not possible. Okay, so we cannot like reconstruct this eigenvector of this covariance matrix. So whatever, now see, this wk is the eigenvectors. This is the important part, guys. This is now I am explaining. So this is now the important part of the kernel PCA, okay, and our normal PCA. We are trying to get wk every time. We are saying I want wk because this line I want to draw, I want to draw. Like, okay, that's okay if you are doing PCA, that's fine. But your PCA is not the one operation. It is just kind of a pre-processing. In your complete video pipeline, if you are doing some big work or big project or big object detection, so your PCA is somewhere here in the pre-processing thing, and your actual algorithms, whatever detections will happen, these algorithms are in the here. This is like kind of a classifier. Okay, and this PCA is giving, this is for example SVM, this, and this is like a detection. So in the downstream, your algorithm is simply a algorithm which has to give some input to the SVM. You no need to draw this kind of a line, because SVM is not interested in the line. SVM work is actually drawing the line, not the PCA work. PCA has to give me some kind of a way, some kind of a direction where the maximum variance is happening. Give me the direction where the variance is happening. I am not interested in the line and all. That I will do. That SVM say I will do that. I am not interested in drawing the line. You give me something what you are now having. So I am happy with that. So okay. So here with this approach, calculating wk from phi of x and lambda k, So that you can't do this step, that you cannot do this step, because this calculation of phi of x is coming, and phi of x is like having the time complexity of d raised to p. Okay, dimension raised to that whatever the power you are projecting in the higher dimension. So that's the bigger complexity. So we cannot reconstruct the eigenvector. You cannot do the wk calculation. Eigenvector of that covariance matrix, okay, of that covariance matrix. You cannot reconstruct the eigenvector of that covariance matrix. Okay, because phi of x is not at all possible. Okay, but the point is, it's okay if I cannot draw the line, it's okay, but what I can do, so if you see in our basic PCA, I just draw also last time, what is the lines, these are the points. Okay, these are the points. Okay, this is the point, you try to understand this one. Okay, this is the point which you will take forward also in all kind of operations, SVM and all. You have the line, these points. What you are doing, you are finally, okay, finally projecting the points on this. There is something, some line or something here, or you are just trying to get this line here. You are projecting the points on this line, and then you will forget about these actual point. Okay, once you get this, once you get the, maybe I'll use some other here. Once you get the projections, you are now forgetting about the actual points. You are like, leave this point, I am not interested now this point. Like you are just saying that remove this point, because you already got that points. Okay, so you already got that. So okay, so it's saying that I'm not interested into the points now, the actual points. I'm happy with the projections, whatever the projections I have done, this x, whatever the x it was, no, not interested. Now it is actually what, w transpose x, this value. You are interested into w transpose x, you are not interested into this x. Okay, you are not interested into the phi of x, you are interested into this projection of that. What is w? W is your eigenvector. What is that eigenvectors? Vectors, whatever you are doing this calculation. Okay, what is that? This is, in our earlier term we calculate beta, correct? This alpha, you calculated alpha. These are your eigenvectors in these earlier terms, and this, what this gives you, this w. You got this? Did you understand this? We are not now interested into this x value here. You are projecting here on this line, and you forget about x now. You forget about the x. You forget about this x, because this x is now gone. Its projections is there, and this projection is what? In the lower dimension, in normal case, we know that this projection is w transpose x. But now it is in higher dimension. So higher dimension is what? X is what? X is like phi of x. You are projecting the higher dimension. And what is w? W is nothing but your eigenvector, that what we have calculated in the step number 3 here, this alpha. Okay, this is alpha x, alpha kj, like for example is alpha kj. Like I need to put into this summation symbol, so I need to do the addition of all these things. So I am now interested in these projections, not in the points which are now here. Okay, so what is now happening, what we are now doing here. So yeah ma'am, 10 minutes ma'am. Okay, 10 minutes, that's all. Okay, so this is something, now it's going to be done now. So you are now taking this phi transpose of xi, because I just mentioned, okay, into wk, like if I say like this, okay, this is nothing but phi transpose of xi into wk. Like if I say, consider this like a normal earlier case, okay, this is nothing but this has the this is the kth most important number, like the kernel's most important number corresponding to the data point, to data point xi. Means you are not thinking about this xi, you are just thinking about this projection, and this projection gives you the some important information about your xi. Now your xi is gone, and what this actually give you, what this point will actually give you, once you project this point on the line here, this will give you some part, some of their that point will give you some of their contribution to the variance. Okay, so if I'm saying that this is the variance of that, so this variance, say that okay, this is the variance, means this point is come from this here. So the variance gives the points or the proxies or the projections, or the proxies of the point which have some or little amount of contribution to the actual variance. And once you get the variance, that is nothing but your, if it is like a maximum variance, that is what, that is nothing but your line indirectly, that is nothing but your some kind of line which just try to like give you the difference between, like just try to say that okay, in higher dimension it try to give you the linear relationship of the data points. And what is this? This is nothing but the variance, and that variance is what you are getting from these proxies. So here, okay, so what now happen here, phi transpose of xi into wk is what, phi transpose of xi, and what is that wk? Wk is what, now we know that this is like a wx is equal to what, capital X into alpha x, for example, okay, alpha. This is what we found in earlier when the points are linear, but in this case what, this wk is what, you are just adding all these proxies 1 to n, phi of xj into alpha of kj. Okay, this is what your, because I mentioned it, this w into x, w transpose x or x transpose w is the same. Okay, so this is here. Okay, and this value is nothing but, because I am now taking everything inside, this phi of xi I am just taking inside, because this is summation of j equal to 1 to n. So this alpha kj as it is, or xi now here, phi of this phi of xi transpose, and this phi of xj here, phi of xj. What is this phi of xj? Now you know that this is what, this is the kernel. We know that this is the kernel. This is the kernel k I window j. That's all. So you are trying to get the proxies instead of drawing the line, but drawing the line is nothing but just for the showcase or showing the PCA output. It's okay. Okay, but we are not actually stopping at PCA. We are going further, and we just need some kind of a maximum variance direction, the direction where we can see the maximum variance, and each point which is like here, the point which is in the space you are dropping here, and this give you some of their contribution to the variance of this line here, the, or I don't say line but variance here. Okay, this gives the some of their contribution here. And what is this? This is nothing but your x, this is nothing but your phi transpose phi, this point is nothing but what, this point is nothing but your phi transpose xi into wk. And that wk, if I just do that, if I want to get the proxy in the higher dimension, this is not in lower dimension, okay, it is in higher dimension, that is nothing but your summation of j equal to 1 to n, this alpha kj, whatever the alpha value you calculated, alpha k into I into k of I into j. That's all. Once you get these kind of a proxies, then you will get the variance. So okay, once you get this kind of a proxy values like the alpha, this value, once you get this one, this is nothing but your variance value. This is nothing but giving you the variance value, and that will give you the kind of linear relationship or kind of a line where you are supposed to drop your all the points in the higher dimensions. Okay, so it is something. If I just say this modified step, like whatever modified, I will just, we have now modified this step number 4. Okay, so the same thing whatever now I just showed you now, the projection of this xi onto the kth principal component, because see these are the principal component, whatever you need to do like a projection of this point on this first, or say maybe this is kth principal component, you need to project this one here. So this is what x transpose or w transpose x. Okay, this is what you are doing here. So here something same way you are doing summation of j equal to 1 projection of xi onto the kth principal component. We are getting like alpha of k j into k of ij for all value of k. That's all. Means what, this is nothing but you are calculating j equal to 1 and alpha of 1 j into k of ij. This is same, second is j equal to 1 to n alpha 2 of j into k of ij, like so on till j equal to 1 to n alpha of so it's like a l into j, sorry, it's like a proper, it's like 1, it's l here into k of ij. These are your proxy points. Okay, this is nothing but your proxy point. This is one proxy point, this is next proxy point. Means whatever in higher dimensions you can see that this is like this point, one point. Okay, this is the one point here, the another point is here, this third point will be somewhere here, like the L, this is L last point, L point, so L point will be, so you are just actually projection, you are doing this projectioning the xi point on the given kth principal component. Okay, so this is what you are doing, and this is the way how we actually do this principal component analysis in the kernel PCA. So this modified step is important. Okay, this modified step, how you got that, you understood now here. This modified step is what you are trying to get the projections. You are not now behind this line drawing the line, you are trying to get, instead of line you are happy with the projections, like give me the projections. Once I get the projections, I understood that how much that projection contributed in the variance. That's all. If that projection contributed more in the variance, and that if like you are having more and more points on the variance, means actually this side this variance is more, and indirectly you are saying that this is a line because the variance along this side is more. So finally you are saying variance is the best one here, so this is the line, and once you get the line you will give this input to the next algorithm like SVM or another classifier in the downstream, and that will give you the actual object what you want to do. So this step should be remembered, like you are calculating alpha 1, alpha 2, alpha 3, alpha L. Okay, and this is like summation of j equal to 1 to L. Yes, this step has to be remembered. Okay, and this is actually into, this is multiply kij. Okay, this is a modified step number 4, because our earlier step was here, that step 4, that calculation of wk, which is not allowed. So for not allowing this one, wk calculation is not allowed, you don't want this actual line. So instead of getting line, you calculate the variance, and that variance is nothing but your calculation of this step number 4. And how we, this modified step we got, it's something like here, because I mentioned you every point is projected here on this point is now phi of x. That's all. So this is the most important number corresponding to the data point. So like as I mentioned, these are the projections which contribute to the variance. So you need a variance. Indirectly you are, the variance will give you the best line, and hence this is what the kernel PCA do. And this is the setup here. So if you see here, so I'm doing the centering the data, eigen decomposition, calculated eigenvalue, eigenvectors. And you know, like, oh sorry, I think I did that also, yeah. So here if you see this alpha is like, you are normalizing it under root of n lambda u, because you know that we are interested in the eigenvectors having length equal to like the normalization. We know that the center should be with the length of 1, so that's why we are normalizing. So this vector divided by the square root of your eigenvalues. And if you do the calculation here, this normalization steps is happening here, yeah, case centered, and okay, this one is happening here. And I'm actually then you projecting that data by using two principal components here. So so here you can see this component 1 versus component 2. I'm just plotting the graph. So earlier circular whatever the moon data set, this is like having non-linear relationship. Now it is showing some kind of a linear relationship, but this is what the output of PCA, and PCA will give this output to the next step like SVM. SVM will train that and it try to see that okay, which is the best line. And then SVM say that okay, this side is the different data set and this side is different. Means given data set has this side people less salary, and this side people is having more salary. Means like you can just do later on any analysis and see that how you can differentiate the two different data set which are not linear, but you make it non-linear to linear using PCA, using kernel PCA. So this is what kernel PCA, and week 2 ends, and this way we successfully finished our first unsupervised learning algorithm called as PCA. Okay, so any question till now? Okay, no problem. You can maybe, yeah, see the video later. You